Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Take a moment to settle in, to let the day finally release its grip. Let your breathing slow just a little. Where in the world are you watching from? A quiet bedroom where the night has already settled? A cozy corner where you're finally alone with your thoughts? Wherever you are, you're exactly where you need to be. Tonight we're going to explore something truly remarkable. 26 light-years from Earth, the James Webb Space Telescope has found something that scientists are calling one of the most significant discoveries in the history of astronomy. A planet named K218b, orbiting a small red star in the constellation Leo. Not just any planet, but a world that might harbour life. Not someday, not theoretically, but right now. The data suggests a 99.7% probability that this world could support living organisms. We'll discover what makes this distant planet so special, understand the strange chemistry detected in its atmosphere, and contemplate what it might mean if we're truly not alone in the universe. But don't worry, this isn't going to be a breathless race through sensational headlines or wild speculation about alien civilizations. Instead, we'll move slowly and carefully through the science, the discovery, the implications, taking our time with each piece of evidence. By the end, I think you'll find a kind of peace in knowing that the universe might be more alive than we ever imagined, and that this knowledge somehow makes our own existence feel both smaller and more precious. If you enjoy these calm explorations of the cosmos, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being here, for trusting me with these quiet hours. So settle in, let your shoulders drop, take a slow breath, and feel it fill your lungs completely before you release it. Let's begin our slow drift through the story of K218b. There's nowhere you need to be right now, nothing you need to do. Just listen and let the story unfold like starlight reaching Earth after travelling for millions of years, patient and inevitable and gentle. K2-18b exists as a world we cannot see with our naked eyes, circling a star called K2-18, a red dwarf much smaller and cooler than our own Sun. This star sits in the constellation Leo, that great celestial lion that stretches across the spring sky 26 light-years away. In cosmic terms, K2-18b is practically our neighbour, one of the closest potentially habitable worlds we've yet discovered. The star K2-18 is what astronomers call an M-dwarf, a category of stars that make up about 70% of all stars in our galaxy. These stars burn slowly and steadily, living for trillions of years compared to our Sun's mere 10 billion year lifespan. K2-18 itself has a mass only about 1/3 that of the Sun, and it shines with a reddish glow that would make any sky beneath it appear alien to our eyes. The planet K2-18b was first discovered in 2015 by NASA's Kepler Space Telescope, which found it through the transit method, watching as the planet passed in front of its star and caused the star's light to dim ever so slightly. That initial discovery told astronomers the planet's size and orbital period. K2-18b is what we call a sub-Neptune, a world larger than Earth but smaller than Neptune. It's roughly 8.6 times Earth's mass, and about 2.6 times Earth's radius. It orbits its star once every 33 Earth days, close enough to receive a similar amount of energy from its star as Earth receives from the Sun, despite the star being so much cooler and dimmer. What makes K2-18b particularly interesting is that it sits squarely in its star's habitable zone, that precious region where temperatures allow liquid water to exist on a planet's surface. For years after its discovery, K2-18b remained just another entry in the growing catalogue of exoplanets. Interesting, but not remarkable. Astronomers knew it was there, knew its basic properties, but understanding the nature of such a distant world required tools that simply didn't exist yet. The planet remained a mystery, a world defined by what we didn't know rather than what we did. The James Webb Space Telescope changed everything. Launched on Christmas Day in 2021 and deployed at a point in space called L2, about 1 million miles from Earth, Webb possesses infrared vision far beyond anything humanity had built before. When Webb turned its golden mirrors toward K218b in 2023, it didn't look at the planet directly. Instead, it watched as the planet transited its star, and it analysed the starlight filtering through the planet's atmosphere. That light, broken into its component wavelengths, revealed the chemical fingerprints of the gases surrounding K2-18b. And what Webb found sent ripples through the astronomical community, a discovery that would transform K2-18b from catalogue entry to one of the most intriguing worlds in our cosmic neighbourhood, a planet that might, just might, be home to life. When starlight passes through a planet's atmosphere during a transit, the gases in that atmosphere absorb specific wavelengths of light, leaving dark lines in the spectrum. Each molecule absorbs light at characteristic wavelengths, creating a unique fingerprint that allows astronomers to identify which chemicals are present even across vast distances. This technique, called transmission spectroscopy, is one of humanity's most powerful tools for studying worlds we can never visit. The James Webb Space Telescope observed K2-18b for multiple transits, gathering data with its near-infrared spectrograph, an instrument so sensitive it could detect the faintest chemical signatures. The initial data revealed what astronomers expected to find in a sub-Neptune atmosphere: hydrogen and helium, the most abundant elements in the universe, forming a thick envelope around the planet. But then the unexpected appeared in the data. The spectrum showed clear evidence of methane and carbon dioxide, molecules that told a story of a very different kind of world than astronomers had anticipated. Most sub-Neptunes that had been studied showed atmospheres dominated by hydrogen, with little else detectable. The presence of significant methane and carbon dioxide suggested something unusual about K2-18b's atmosphere, a chemistry that didn't fit the standard models. Even more intriguing, the data showed a notable absence of ammonia. This might seem like a strange thing to get excited about, what wasn't there, but in atmospheric chemistry, absences can be as revealing as presences. Computer models of planetary atmospheres predict that in a hydrogen-rich atmosphere, any methane should react with nitrogen to form ammonia. The fact that K2-18b showed methane but no detectable ammonia suggested that either the atmosphere contained very little nitrogen, or that conditions in the atmosphere were destroying ammonia as fast as it formed. The most exciting explanation for this chemical signature involves liquid water. If K2-18b has a global ocean beneath its hydrogen envelope, that ocean could be dissolving the ammonia, removing it from the atmosphere while allowing methane and carbon dioxide to persist. This scenario, if correct, would mean K2-18b is what astronomers call a Hycean world, a type of planet theorized but never before detected. A hydrogen atmosphere planet with a liquid water ocean. The spectrum revealed one more tantalizing detail, though this one remains more tentative, requiring further observation to confirm. In the data, there appeared to be a signature consistent with dimethyl sulfide, a molecule that on Earth is produced almost exclusively by living organisms, particularly by phytoplankton in the ocean. The detection wasn't strong enough to be certain. The signal could be noise or could be caused by other processes, but if confirmed, it would represent something extraordinary. Dimethyl sulfide breaks down relatively quickly in atmospheres, destroyed by ultraviolet light and chemical reactions. For it to be present in detectable amounts, something would need to be continuously producing it. On Earth, that something is life. Billions upon billions of microscopic organisms releasing this sulfur compound as a byproduct of their metabolism. Finding it on K2-18b would suggest strongly that similar biological processes might be happening there. The science team that analysed this data was careful, appropriately cautious in their conclusions. They published their findings in respected journals, noting both what the data clearly showed and what remained uncertain. The presence of methane and carbon dioxide was definitive. The absence of ammonia was confirmed. The possible detection of dimethyl sulfide was labelled as tentative, requiring additional observations to verify. But taken together, these findings painted a picture of a world utterly unlike any we'd studied before, and perhaps remarkably similar to our own. The term Hycean is relatively new to astronomy, coined only in 2021 by a team of researchers led by Niku Madhusudhan at Cambridge University. It's a portmanteau of hydrogen and ocean, describing a theoretical class of planet that could be far more common in the galaxy than Earth-like rocky worlds, and potentially far more hospitable to life than anyone had previously imagined. Traditional thinking about habitable planets focused almost exclusively on rocky worlds similar to Earth, with thin atmospheres of nitrogen and oxygen, liquid water on the surface and a solid ground beneath. We looked for Earth twins because Earth was our only example of a living world, but this narrow focus might have caused us to overlook an entirely different category of habitable environments. Hycean worlds are sub-Neptunes, planets that form beyond the ice line in their stellar systems where water ice and other volatiles are abundant. They grow large enough to capture thick hydrogen atmospheres from the protoplanetary disk, but not so large that they become full gas giants. Beneath that hydrogen envelope, the tremendous pressure and relatively warm temperatures can maintain a global ocean of liquid water. The key insight that makes Hycean worlds potentially habitable is that life doesn't need oxygen to exist. Oxygen is actually toxic to many of Earth's organisms, particularly those that evolved in the planet's early history, when the atmosphere contained almost no oxygen at all. Many microorganisms thrive in environments completely devoid of oxygen, getting their energy from chemical reactions involving hydrogen, methane, sulfur compounds, or other elements. A thick hydrogen atmosphere, rather than being hostile to life, could provide exactly the chemistry that certain types of organisms need. Hycean worlds potentially offer several advantages over Earth-like planets when it comes to hosting life. Their larger size means they can retain thick atmospheres even around active stars that might strip away thinner atmospheres. Their deep oceans would provide stable temperatures and pressures, buffering the surface against the variations in stellar output that could make smaller planets uninhabitable. The presence of hydrogen in the atmosphere could provide a potent energy source for organisms that know how to use it. 3 subtypes of Hycean worlds have been proposed based on their distance from their star and the resulting temperature conditions. Standard Hycean worlds orbit close enough to their star to receive moderate heating, maintaining liquid water at habitable temperatures. Cold Hycean worlds orbit farther out, receiving less stellar energy, but could still maintain liquid oceans beneath ice-covered surfaces, similar to Jupiter's moon Europa or Saturn's moon Enceladus. Dark Hycean worlds are tidally locked to their stars, with one side perpetually facing toward the star and the other facing away, potentially creating habitable conditions on the dark side where temperatures would be cooler and more stable. K218b appears to be a standard Hycean world. It receives roughly the same amount of energy from its star as Earth does from the Sun, though that energy comes in different wavelengths due to the cooler nature of its red dwarf star. Models suggest temperatures on K218b could range from 10 degrees Celsius to 40 degrees Celsius, well within the range where liquid water remains stable and where Earth's organisms thrive. The ocean beneath K2-18b's hydrogen atmosphere could be hundreds of kilometres deep, far deeper than Earth's oceans, with pressures increasing toward a high-pressure ice layer at the bottom, or possibly even a rocky core. The exact structure depends on the planet's composition, which remains uncertain, but the presence of methane and carbon dioxide in the atmosphere suggests active chemistry, either geological or biological, cycling these molecules between the ocean and the atmosphere. What makes the Hycean concept so important is its implications for the prevalence of habitable worlds in the galaxy. Sub-Neptunes are the most common type of planet we've discovered, far more abundant than Earth-sized rocky worlds. if even a fraction of these worlds have the right conditions to maintain liquid water oceans, the number of potentially habitable environments in the galaxy could be orders of magnitude higher than previous estimates suggested, and K218b might be our first glimpse of what could be a vast cosmic ocean of possibility. Dimethyl sulfide is not a familiar molecule to most people, but in the search for life beyond Earth, it has become one of the most exciting chemicals astronomers could hope to find. On our planet, dimethyl sulfide, often abbreviated DMS, is produced primarily by phytoplankton, the microscopic photosynthetic organisms that drift in the ocean and produce much of Earth's oxygen. These organisms create DMS as they process sulfur compounds, releasing it as a waste product into the water, from where it escapes into the atmosphere. The atmospheric signature of dimethyl sulfide is distinctive. It absorbs light at specific infrared wavelengths, creating a pattern that doesn't match common abiotic molecules. When the James Webb team analysed K218b's spectrum, they found a feature that aligned with DMS absorption, though the signal was not overwhelmingly strong. The wavelength matched, and the strength of the absorption was consistent with what models predicted for a Hycean world producing DMS at rates similar to Earth's oceans. But here's where scientific caution becomes essential. A single spectral feature, even a compelling one, is not proof of anything. Spectra can be noisy, and features can appear that look like one molecule, but are actually caused by something else entirely. Other processes could potentially create similar absorption patterns. Photochemistry in the upper atmosphere might produce sulfur compounds that mimic the DMS signature. Volcanic activity, if K218b has an active geology, could release sulfur-containing gases that create confusion in the data. The science team acknowledged these uncertainties directly in their published papers. They calculated the probability that the DMS feature was real rather than noise, and found it statistically significant but not overwhelmingly so. They outlined what additional observations would be needed to confirm or refute the detection. They emphasized that this was a tentative finding requiring verification, not a definitive discovery of alien life. What makes the potential DMS detection so intriguing is not just its presence, but its context alongside the other atmospheric findings. Methane and carbon dioxide together create a reducing atmosphere, one that's chemically active and could support metabolisms based on hydrogen and carbon chemistry. The absence of ammonia suggests a process removing it from the atmosphere, possibly dissolution in a water ocean. And if dimethyl sulfide is truly present, it would need to be continuously replenished, because DMS breaks down relatively quickly in atmospheres exposed to ultraviolet light. On Earth, the ocean produces about 30 million tons of dimethyl sulfide each year. This might sound like a lot, but spread across the entire planet, it creates only a small signature in our atmosphere. Yet even that small amount plays significant roles in Earth's climate and chemistry. DMS molecules released from the ocean rise into the atmosphere where they oxidize, forming tiny particles that seed cloud formation. Those clouds reflect sunlight back into space, cooling the planet. It's a feedback loop where life influences climate, which in turn influences the conditions for life. If K218b has organisms producing DMS, they would likely be very different from Earth's phytoplankton. The environment is different, with a hydrogen atmosphere instead of nitrogen and oxygen, with different wavelengths of light penetrating from the red dwarf star, with different pressures and temperatures and chemical conditions. Yet the basic chemistry of life might be universal enough that sulfur metabolism could evolve independently, creating similar compounds as byproducts. The 99.7% probability mentioned in headlines comes from a statistical analysis combining all the atmospheric findings, not from the DMS detection alone. Models that include a Hycean ocean with biological activity match the observed spectrum much better than models without life, creating a very high probability that K2-18b could support living organisms. But probability is not certainty. And scientists know well that high probabilities have been wrong before. The universe has surprised us repeatedly with its creativity in producing abiotic processes that mimic biology. Still, the data is compelling enough that K218b has become a priority target for future observations, a world that warrants our closest attention as we continue studying it. And this brings us gently to the question of what more we might learn. K218, the star that K218b orbits, belongs to a class of stars that astronomers have come to view with both hope and concern when considering the possibility of life elsewhere. Red dwarfs are small, cool stars, burning their nuclear fuel so slowly that they can shine for trillions of years, lifetimes far exceeding the current age of the universe. They're also the most common type of star in the galaxy, making up perhaps 70 to 80% of all stars. If planets around red dwarfs can host life, then habitable worlds might be extraordinarily common in our cosmic neighbourhood. But red dwarfs present challenges that make habitability complicated. These stars are often quite active, particularly when young, producing powerful flares that blast their planets with intense radiation and high-energy particles. A flare from a red dwarf can increase the star's brightness by factors of 10 or more in just minutes, bombarding any nearby planets with ultraviolet and X-ray radiation that could strip away atmospheres and sterilize surfaces. K218 appears to be a relatively calm red dwarf, at least by the standards of its type. Observations show some stellar activity, occasional flares and variations in brightness, but nothing catastrophic. The planet's thick hydrogen atmosphere might actually provide protection, absorbing and scattering the high-energy radiation before it can reach the ocean below. This is one advantage Hycean worlds might have over rocky planets with thin atmospheres, a built-in radiation shield. Another challenge red dwarfs present is the nature of their light. These stars emit most of their energy in infrared wavelengths, rather than the visible light our eyes evolved to see. Any organisms using photosynthesis on a planet around a red dwarf would need to have evolved different light harvesting systems, different photosynthetic pigments that could capture the longer wavelength photons efficiently. On Earth, we have organisms that use infrared photosynthesis, certain bacteria that thrive in low-light conditions, proving that life can adapt to dimmer, redder illumination. The closeness of habitable zone planets to red dwarf stars creates another interesting effect. Planets orbiting this close often become tidally locked, with one side perpetually facing the star and the other side facing away into eternal darkness. Earth's moon is tidally locked to Earth, which is why we always see the same face. For K2-18b, tidal locking would mean one hemisphere receiving constant illumination, while the other remains forever in shadow. This might sound like it would make the planet uninhabitable, creating temperature extremes between the day side and night side that would make the planet hostile to life. But for a Hycean world with a thick atmosphere and deep ocean, tidal locking might not be fatal. The atmosphere and ocean would transport heat from the day side to the night side, moderating temperatures across the planet. Some models suggest the terminator region, the boundary between day and night, could be the most hospitable part of a tidally locked world, receiving gentler illumination and more stable temperatures than either the blazing day side or frozen night side. We don't know for certain whether K2-18b is tidally locked. The orbital period of 33 days is short enough that tidal forces have likely slowed the planet's rotation significantly, but it might still maintain a slow rotation rather than being fully locked. Future observations might reveal this by looking for variations in the atmosphere as different hemispheres of the planet rotate into and out of view during transits. The proximity of K2-18b to its star, just 26 light-years from Earth, makes it one of the closest potentially habitable worlds we've discovered. There are closer planets, certainly. Proxima Centauri b orbits the nearest star to our Sun at just over 4 light-years away, and it too lies in its star's habitable zone. But Proxima Centauri is an extremely active red dwarf, and questions remain about whether its planet could maintain an atmosphere against the onslaught of stellar radiation. K2-18b, with its thick hydrogen envelope and more sedate star, might be a gentler environment, more conducive to the slow, patient work of biology. 26 light-years translates to about 150 trillion miles, or about 250 trillion kilometres. It's a distance so vast that light, travelling at 186,000 miles per second, takes 26 years to cross it. The light we're seeing from K218 today left that star in 1998. If there are organisms in K218b's ocean producing dimethyl sulfide right now, at this very moment, we won't see evidence of that in the starlight for another 26 years. And yet, in cosmic terms, 26 light-years is nothing, barely beyond our stellar doorstep, close enough that some astronomers have already begun imagining what it would take to send a probe there. And this thought carries us gently forward into contemplating what such a journey might entail. The James Webb Space Telescope represents humanity's most ambitious attempt to see the universe in infrared light. Its primary mirror, composed of 18 hexagonal segments coated in gold, spans 6.5 meters across, making it the largest mirror ever launched into space. Each segment can be individually adjusted by tiny motors, aligning the entire mirror to a precision measured in nanometers, far thinner than a human hair. Gold was chosen for the mirror coating because gold reflects infrared light with extraordinary efficiency. Better than 98% of the infrared photons that strike it bounce back rather than being absorbed. This matters enormously when trying to capture the faint infrared glow from distant objects. Every photon counts when you're trying to detect the chemical signature of an atmosphere around a planet hundreds of trillions of miles away. Webb doesn't orbit Earth the way the Hubble Space Telescope does. Instead, it sits at a special point in space called the second Lagrange point, or L2, about 1 million miles away from Earth in the direction opposite the Sun. At this location, the gravitational pulls of the Sun and Earth balance, in a way that allows Webb to orbit the Sun in sync with Earth, maintaining a relatively fixed position in space. This location is ideal for infrared astronomy. Webb needs to be cold, very cold, to detect the faint infrared signals from the universe. Heat is infrared radiation, and if the telescope itself were warm, its own heat would overwhelm the signals it's trying to detect. At L2, Webb can deploy a tennis court-sized sunshield that blocks light and heat from the Sun, Earth and Moon simultaneously, allowing the telescope and instruments to cool to temperatures around 40 degrees above absolute zero, cold enough that the telescope's own heat doesn't interfere with its observations. The near-infrared spectrograph. The instrument that observed K218b is one of 4 main science instruments aboard Webb. It can split incoming light into spectra covering wavelengths from 600 nanometers to 5,000 nanometers, spanning from the visible red into the infrared. It's specifically designed to study transiting exoplanets, with modes optimized for capturing the transmission spectra as planets pass in front of their stars. When K218b was selected as a target, the telescope had to be carefully oriented to point at the star in Leo. The scheduling is complex because Webb can only observe certain parts of the sky at certain times of year, limited by the need to keep the sun shield between the telescope and the Sun. The observations had to be timed to coincide with K218b's transits, those roughly 6-hour periods when the planet passes between us and its star. Multiple transits were observed to build up enough signal to detect the faint atmospheric features. Each transit provided one data point, one spectrum showing how the starlight was filtered through K218b's atmosphere. By combining multiple transits, astronomers could average out the noise and reveal the underlying chemical signatures with greater clarity. The data that came back from Webb was not immediately interpretable. Raw spectroscopic data requires extensive processing to remove instrumental effects, correct for stellar variations, and extract the planetary signal from the much brighter stellar background. The teams who analysed K218b's data spent months carefully processing the observations, running multiple independent analyses to verify that the features they were seeing were real and not artifacts of the data reduction process. The methane and carbon dioxide signatures emerged clearly from this analysis. These were robust detections, showing up consistently across different reduction methods and different analysis techniques. The absence of ammonia was similarly clear. The tentative dimethyl sulfide feature was more subtle, appearing in some analyses but not others, strong enough to be intriguing, but not definitive enough to be certain. Science thrives on this kind of careful, methodical work. The headlines might announce dramatic discoveries, but the reality is thousands of hours of painstaking analysis. Checking and rechecking, looking for errors, considering alternative explanations, building statistical models to understand what the data truly shows. The researchers studying K218b did this work with admirable rigour, publishing detailed papers describing their methods and uncertainties, inviting other scientists to examine their data and draw their own conclusions. When scientists say there's a 99.7% probability that K218b could support life, they're making us. Before we continue, I want to pause for just a moment, because what you have learned in the last 30 minutes is something genuinely rare. Most people move through their entire lives without ever stopping to understand the world at this level, but you did. Tonight you chose curiosity over noise and depth over distraction. That is exactly who this channel was made for. If you want to keep being that person, a like and subscribe takes 2 seconds and make sure this channel never stops finding you. Now, let's go deeper. They're making a statement based on Bayesian statistical analysis, a mathematical framework for updating beliefs based on new evidence. This kind of probability doesn't mean we're 99.7% certain that life exists on K2-18b. Rather, it means that the atmospheric chemistry we observe is 99.7% more likely to occur if the planet has biological activity than if it doesn't. The calculation works by comparing different models of K2-18b's atmosphere. One model includes only abiotic processes, geological and chemical cycles with no biology. Another model includes the same abiotic processes, plus the addition of organisms that produce methane and dimethyl sulfide through their metabolism. Each model makes predictions about what chemicals should be present in the atmosphere and in what proportions. The models are run thousands of times, varying the input parameters within reasonable ranges to explore the space of possibilities. Some abiotic models might produce lots of methane through geological processes like serpentinization, where water reacts with certain types of rock. Other models might produce methane through photochemistry in the upper atmosphere. The question is whether any of these abiotic scenarios can match the observed spectrum as well as the biological model does. What the analysis found is that abiotic models struggle to explain the full suite of observations simultaneously. Getting the right amount of methane while avoiding ammonia production is difficult, without invoking a water ocean to dissolve the ammonia. Producing detectable amounts of dimethyl sulfide abiotically, while not impossible, requires specific and somewhat unlikely conditions. The biological model, where organisms in a water ocean consume hydrogen and carbon dioxide, produce methane as a waste product, process sulfur compounds and release dimethyl sulfide, matches the data more readily. The 99.7% figure represents the ratio of these probabilities. The biological model is about 300 times more likely to produce the observed spectrum than the best abiotic models. In Bayesian terms, this is strong evidence, though not absolute proof. A 300 to 1 ratio is compelling, but it's not infinite. There remains that 0.3% chance that we're misinterpreting the data, that some abiotic process we haven't considered is producing these signatures. Scientists are appropriately cautious about such probabilities because the history of astronomy is filled with examples of phenomena that seemed biological but turned out to be natural. The canals of Mars observed by astronomers in the late 19th and early 20th centuries were thought by some to be evidence of Martian civilization. They turned out to be optical illusions. Pulsars, when first discovered in 1967, were initially dubbed LGM-1 for little green men. because their regular pulses seemed too precise to be natural. They turned out to be rapidly rotating neutron stars. The difference with K218b is that modern astronomers are not claiming to have found life. They're presenting evidence that is consistent with life, while acknowledging that confirmation requires additional observations and additional data. The 99.7% probability is not a declaration of discovery, but a statement about which models best fit the current data and an invitation for more scrutiny. Future observations will test this probability. If K218b truly has biology, then repeated observations should consistently show the same atmospheric signatures and might reveal additional biosignatures. Seasonal variations might appear if the biology responds to changes in stellar illumination or other environmental factors. The dimethyl sulfide signal, if real, should remain detectable or even strengthen with better data. If the probability is misleading, if the signatures are actually abiotic, then more detailed observations might reveal inconsistencies, spectral features that don't match biological models, or variations that suggest geological rather than biological sources. Science is self-correcting, and the community studying K2-18b is actively working to determine which interpretation is correct. What makes this probability so intriguing is not that it's close to 100%, but that we're able to calculate it at all. Just 20 years ago, we had no confirmed exoplanets and no way to study their atmospheres. 10 years ago, we could barely detect the presence of atmospheres around exoplanets, let alone characterize their chemistry. Now we're at the point where we can not only identify the molecules present in distant atmospheres, but also evaluate whether those molecules might be signs of life. The math of probability gives us a framework for thinking about uncertainty in a rigorous way. It allows us to distinguish between possibilities that are merely conceivable and possibilities that are probable based on evidence. For K218b, the evidence points towards something remarkable, something that warrants our careful attention and our best efforts to understand what we're truly seeing, and this brings us naturally to consider what other telescopes might add to our understanding. The James Webb observations of K218b represent a beginning, not an end. The telescope has already been scheduled for additional observations of this intriguing world, observations that will look at the planet in greater detail and across additional wavelengths. Each new dataset will either strengthen the case for a Hycean world with biosignatures, or reveal alternative explanations for what we're seeing. One key question future observations will address is the tentative dimethyl sulfide detection. Webb spectrographs can observe at higher spectral resolution, breaking the light into finer wavelength bins that might reveal the DMS signature more clearly. If DMS is truly present, its spectral fingerprint should become more definite with better data. If the feature is noise or caused by something else, higher resolution might make it disappear or reveal it to be a different molecule entirely. Another critical observation will look for other potential biosignatures. On Earth, living organisms produce a variety of gases that accumulate in the atmosphere. Oxygen is the most obvious, created by photosynthesis, and sustained at high levels only because plants and algae continuously produce it. Methane is another, created by methanogenic bacteria in oxygen-free environments. When oxygen and methane exist together in an atmosphere, it's a powerful biosignature because these gases react with each other and should disappear unless something continuously replenishes them. K218b's hydrogen atmosphere means we won't find oxygen there. Oxygen would react explosively with hydrogen, but other biosignatures might be detectable. Certain sulfur compounds besides dimethyl sulfide are produced by life. Phosphine, a molecule of phosphorus and hydrogen, has been proposed as a biosignature for worlds with different chemistries than Earth. Searching K218b's spectrum for these molecules could provide additional evidence for or against biological activity. Webb will also observe K218b at different phases of its orbit, not just during transits. As the planet orbits its star, different parts of its atmosphere and surface come into view. If the planet is tidally locked, observations of its day side, night side, and terminator regions might show different chemical compositions, revealing how heat and chemicals are transported around the planet. These observations use a technique called phase curve spectroscopy, watching how the planet's infrared glow changes as it goes through its orbital phases. Other telescopes will contribute to studying K218b as well. The Hubble Space Telescope has already observed this world, detecting water vapour in its atmosphere in 2019, before Webb's more detailed observations. Hubble operates at different wavelengths than Webb, looking at ultraviolet and visible light rather than infrared. Combined observations from both telescopes provide a more complete picture of the planet's atmosphere. Ground-based telescopes with enormous mirrors and adaptive optic systems might be able to contribute as well. The next generation of extremely large telescopes currently under construction will have mirrors up to 39 metres across, dwarfing even Webb's 6.5 metre aperture. While ground-based telescopes must peer through Earth's atmosphere, which absorbs infrared light, they can observe at certain infrared wavelengths where the atmosphere is transparent, and their enormous light-gathering power might reveal details that even Webb cannot see. The European Space Agency's Ariel mission, scheduled for launch in the 2030s, will be dedicated entirely to studying exoplanet atmospheres. It will observe hundreds of planets, including K2-18b, characterizing their chemical compositions and looking for patterns across different types of worlds. Ariel will help determine whether Hycean worlds are common or rare, and whether the signatures we see on K2-18b appear on other similar planets. NASA is studying concepts for a future habitable worlds observatory, a telescope designed specifically to search for life on other planets. This observatory would have the sensitivity to detect even fainter biosignatures, and could observe planets at wavelengths optimized for finding atmospheric oxygen, ozone, and other molecules associated with life as we know it. K2-18b, while interesting, is not the ideal target for such a mission, because its thick hydrogen atmosphere prevents us from seeing rocky planet biosignatures. But the techniques developed for observing K2-18b will inform how we search for life on more Earth-like worlds. Each new observation of K2-18b adds pieces to the puzzle, constraining the range of possible interpretations and bringing us closer to understanding the true nature of this distant world. Science progresses through this patient accumulation of evidence, through repeated observations that either confirm or refute our interpretations, through the slow and careful work of distinguishing what we hope to see from what actually exists. It's worth taking a moment to clearly delineate what we actually know about K2-18b from what remains uncertain or speculative. The boundary between knowledge and hypothesis is sometimes blurred in popular accounts, but maintaining that distinction is essential for understanding where the science currently stands. We know with high confidence that K2-18b exists and orbits the star K2-18. This has been confirmed by multiple independent observations showing the regular dimming of the star as the planet transits. We know the planet's size, mass, and orbital period with reasonable precision. We know it receives a similar amount of energy from its star as Earth receives from the Sun, placing it in the habitable zone where liquid water is possible. We know that K2-18b has an atmosphere containing hydrogen, methane, and carbon dioxide. These detections are robust, appearing clearly in Webb's spectroscopic data. We know that the atmosphere lacks detectable ammonia, which is significant given that ammonia should form in a hydrogen-rich atmosphere unless something is removing it. These are not speculations. These are direct observations confirmed by multiple analyses of the data. What we don't know with certainty is whether K2-18b actually has a liquid water ocean. The atmospheric chemistry is consistent with a Hycean model, but consistency is not proof. Other atmospheric structures might produce similar spectral signatures. The planet could have a thick atmosphere with no distinct ocean surface, or it could have a more complex layered structure that we haven't yet modelled correctly. The presence of a water ocean is probable but not confirmed. We don't know whether the tentative dimethyl sulfide detection is real. The signal is tantalizing, but it's at the edge of detectability. It could be genuine, or it could be a statistical fluctuation in the data that will disappear with more observations. Until the DMS signature is confirmed by additional measurements, we should treat it as a possibility requiring verification rather than an established fact. We don't know whether K218b actually hosts life. Even if the DMS detection is confirmed, even if all the atmospheric signatures point toward biological activity, we cannot be certain that life exists there without much more direct evidence. Extraordinary claims require extraordinary evidence, and the claim that we've found life beyond Earth is perhaps the most extraordinary claim in science. We don't know what K218b looks like. We've never taken a picture of this planet. It's too far away and too faint compared to its star for current imaging techniques to resolve it. Everything we know comes from spectroscopy and mathematical modelling. We can imagine what it might look like, a world covered in a deep ocean beneath thick clouds, illuminated by the red glow of its star. But these are mental images constructed from data, not photographs. We don't know whether K218b is tidally locked, though it probably is given its close orbit. We don't know if it has moons, though sub-Neptunes can certainly have satellite systems. We don't know its exact composition, how much of the planet is water versus rock versus gas. We don't know its internal structure, whether it has a molten core or a solid one, whether it has plate tectonics or volcanic activity. These unknowns don't diminish the significance of what we do know. Science proceeds by progressively narrowing the range of uncertainty, by ruling out possibilities and confirming others. Each observation of K218b has reduced our uncertainty, has eliminated some models and supported others. We know vastly more about this planet today than we did when it was first discovered in 2015, and we'll know more still as additional observations accumulate. The honest acknowledgement of uncertainty is one of science's great strengths, not a weakness. It prevents us from overreaching, from claiming more than the evidence supports. At the same time, acknowledging uncertainty doesn't mean all possibilities are equally likely. The evidence we have makes some scenarios far more probable than others, and while we can't be absolutely certain, we can make informed judgments about what K218b most likely is. What we're seeing appears to be a sub-Neptune with a thick hydrogen atmosphere, likely with a water ocean beneath that atmosphere, possibly with biological activity producing methane and dimethyl sulfide. This interpretation fits the data better than alternatives. It's consistent with what we know about planet formation and atmospheric chemistry. It doesn't require any new physics or exotic assumptions, and if it's correct, it represents one of the most significant discoveries in the history of astronomy, the first tentative detection of life beyond Earth, found on a world utterly unlike our own. There's something deeply human about wanting immediate answers, wanting to know right now whether K218b hosts life. But science operates on different timescales than our impatience, and understanding this world will require patience, careful observation, and a willingness to let the evidence accumulate at its own pace. The observations of K218b we've discussed were made in 2023, just months after Webb became fully operational. The analysis took time, with papers published in late 2023 and early 2024. Additional observations were scheduled for 2024 and beyond. Each new dataset requires months of processing and analysis before results can be announced. This is not slow compared to the history of science, it's remarkably fast. But it can feel glacial when we're eager to know whether we're alone. Consider the timeline of exoplanet science itself. The first confirmed exoplanet around a sun-like star was discovered in 1995, just 30 years ago. Before that discovery, we didn't know whether planets were common or rare. We didn't know whether our solar system was typical or unusual. We didn't know whether other stars hosted Earth-sized planets or only Jupiter-sized giants. Those questions have been answered through decades of patient observation. We now know that planets are extraordinarily common, that most stars have planetary systems, that Earth-sized worlds exist in abundance. This knowledge came from thousands of scientists making millions of observations over 3 decades, building telescopes and instruments, developing new detection techniques, learning how to extract planetary signals from stellar noise. The search for life beyond Earth will likely follow a similar timeline. The first tentative detections, like the possible biosignatures on K2-18b, will be ambiguous and will require extensive follow-up. Some promising candidates will turn out to be false alarms, explained by abiotic processes we hadn't fully considered. Others might strengthen, with additional evidence supporting the biological interpretation. Eventually, perhaps within the next 10 or 20 years, we might find a case where the evidence is overwhelming, where multiple independent biosignatures appear on a planet where no plausible abiotic explanation can account for all of them simultaneously. That planet might be K2-18b, or it might be another world we haven't discovered yet. When that moment comes, it will be built on decades of prior work, on lessons learned from studying hundreds or thousands of planets, on improvements in our instruments and our models. The scientists studying K2-18b understand this timeline. They're not racing to declare victory or jumping to conclusions. They're doing what science does best, carefully testing hypotheses, looking for ways to rule out alternatives, seeking observations that can distinguish between competing explanations. This methodical approach might seem frustrating to those of us watching from outside, but it's the only reliable path to truth. There's also beauty in this patience, in the slow unfolding of understanding. If K2-18b does host life, then that life has been there for millions or billions of years, utterly unknown to us, existing in an ocean beneath a hydrogen sky 26 light-years from Earth. It waited that long to be discovered. It can wait a few more years for us to be certain we've truly found it. The light we're seeing from K2-18 left that star 26 years ago, in 1998. The atmospheric molecules that absorbed and scattered that light, creating the spectral features we analyse today, existed then, not now. We're looking into the past, always, when we observe distant objects. If there are organisms in K2-18b's ocean producing dimethyl sulfide at this very moment, we won't see evidence of that for another 26 years. This disconnect between our time and astronomical time is worth contemplating. The universe operates on scales that dwarf human lifetimes. Stars burn for billions of years. Light travels at the ultimate speed limit, yet still takes years or centuries to cross the distances between stars. Planets orbit in cycles measured in days or weeks or years, indifferent to our observations. And yet, despite these vast scales, we can reach out with our instruments and touch these distant worlds. We can analyse light that has travelled for decades and extract from it the secrets of an alien atmosphere. We can determine the chemistry of a planet we'll never visit, inhabited perhaps by organisms we'll never see, living lives we can barely imagine. The patience required for this work is not passive waiting, but active engagement, making observations, analysing data, building models, publishing results, letting other scientists examine and critique the work, refining our understanding incrementally. It's patience in service of knowledge, and there's something profound in that, in our species' willingness to ask questions whose answers might not arrive for years or decades, questions that might not be fully answered in a single human lifetime. K2-18b will still be there, orbiting its red dwarf star whether we're watching or not. The truth about its nature exists independent of our observations. But our slow, patient work to understand that truth is what makes us human, what drives us to build telescopes and launch them into space, to spend careers studying distant worlds, to care deeply about whether life exists somewhere besides our own fragile planet, and perhaps this is what makes the search itself so meaningful. Let's sit with this possibility for a moment. Let's imagine that future observations confirm the biosignatures on K2-18b, that the dimethyl sulfide is real, that the atmospheric chemistry definitively points toward biological activity. What would it mean to know that life exists somewhere besides Earth? The first and most obvious implication would be that life is not unique to our planet. This might seem like a simple statement, but its implications cascade outward in profound ways. If life arose independently on K2-18b, then the universe is not a sterile place with one miraculous exception. It's a place where life can and does emerge given the right conditions, where the chemistry of living systems is written into the laws of physics and chemistry themselves. This wouldn't necessarily mean life is common. K2-18b could be one of only 2 or 3 places in the entire galaxy where life exists. Rare, but not unique. Or it could be one of billions, with living worlds scattered throughout the cosmos like islands in an ocean, each one hosting its own unique biosphere adapted to local conditions. We don't yet know which scenario is correct, but finding even one other living world would rule out the possibility that Earth is alone. The organisms on K2-18b, if they exist, would almost certainly be microbes. The environment there, with its hydrogen atmosphere and Hycean ocean, doesn't seem conducive to complex multicellular life as we know it. Organisms that thrive in high-pressure hydrogen environments would likely be chemotrophs, bacteria or archaea that get their energy from chemical reactions rather than photosynthesis, living in the dark depths of the ocean or in the transition zones between the ocean and atmosphere. These hypothetical organisms would be fundamentally different from Earth life in many ways, yet they would share the basic requirement of all life, the need to harness energy from their environment and use it to maintain organization against entropy. They would have evolved membranes to separate themselves from their surroundings, metabolic pathways to process chemicals, some form of genetic information to pass traits to their offspring. They would be recognizable as life even if they used different biochemistry than Earth organisms. Finding microbial life on another world might seem less exciting than discovering aliens with technology and civilization, but in some ways it would be more scientifically profound. Complex life on Earth took billions of years to evolve from the first simple cells. Intelligence took even longer. But those first cells appeared relatively quickly after Earth became habitable, suggesting that the step from non-life to life might not be as difficult as we once thought. If K2-18b has achieved that step independently, it would support the idea that life emerges readily when conditions allow. The confirmation of life on K2-18b would transform astrobiology from a field rich in theory but poor in examples to a science with multiple data points to study. We could begin to understand which aspects of Earth life are universal and which are accidents of our particular evolutionary history. We could start to develop a more general theory of life, one that encompasses more than the single example we currently have. It would also raise immediate questions about life elsewhere. If K2-18b has life, and if Hycean worlds are common, then how many other living Hycean worlds might exist in our galaxy? Should we turn our telescopes toward other sub-Neptunes in habitable zones, looking for similar biosignatures? The discovery would redirect the search for life, perhaps shifting focus from looking for Earth twins to searching for Hycean worlds that might be far more numerous and easier to study. For human culture and philosophy, the impact would be subtler, but no less real. We've wondered about our place in the universe for as long as we've been capable of wonder. Are we alone, or are we part of a cosmos teeming with life? The answer has oscillated through history. Ancient Greeks imagined other worlds with their own inhabitants. Medieval Christianity saw Earth as unique and central. Modern science has suspected life might be common but lacked evidence. Confirmation of life on K2-18b would settle that question, at least partially. We are not alone. Life exists elsewhere. The universe is not a dead place with one small living exception. This knowledge would change how we see ourselves, our significance, our responsibilities. It wouldn't make us less important, but it would place us in a larger context, part of a biological universe rather than the sole living inhabitants of a sterile cosmos. And there would be an emotional component too, something harder to quantify but perhaps more significant. To know that somewhere in the constellation Leo, beneath a sky illuminated by a red dwarf star, in an ocean we'll never see, organisms are living their lives, metabolizing, reproducing, evolving, completely unaware of our existence just as we were unaware of theirs until recently. There's something profound in that, something that connects us across the void, life calling to life across 26 light-years of empty space. In 1961, astronomer Frank Drake organised the first scientific meeting dedicated to the search for extraterrestrial intelligence. To structure the discussion, he wrote down an equation that attempted to estimate the number of communicative civilizations in our galaxy. The Drake equation, as it came to be known, breaks this enormous question into a series of smaller, more manageable factors. The equation looks like this. N equals R star times Fp times Ne times Fl times Fi times Fc times L. Each variable represents a different factor. R star is the rate of star formation in the galaxy. F-P is the fraction of stars that have planets. N-E is the average number of planets per star that could potentially support life. F-L is the fraction of those planets where life actually arises. Fi is the fraction where life evolves into intelligence. Fc is the fraction where intelligence develops technology capable of communication. And L is the length of time such civilizations remain detectable. When Drake first wrote this equation, we knew almost none of these numbers. We didn't know whether planets were common. We didn't know how many planets per star might be habitable. We certainly didn't know the probability that life would arise or evolve intelligence or develop technology. The equation was more a framework for thinking about the question than a tool for calculation. 64 years later, we've filled in several of these blanks. We know that Fp is close to 1. Nearly all stars have planets. We have good estimates for Ne. Many planetary systems include worlds in their star's habitable zone. Earth-like rocky planets might be less common than we once hoped, but Hycean worlds appear to be abundant. If K218b represents a habitable Hycean world, then Ne might be larger than we thought. The discovery of life on K2-18b would give us our first real constraint on F-L, the fraction of habitable worlds where life actually arises. Currently, this is the most uncertain factor in the equation. Estimates range from nearly 1, if life emerges readily whenever conditions allow, to vanishingly small numbers if Earth's biosphere represents an extraordinarily unlikely fluke. If K2-18b has life, and if that life arose independently rather than being seeded from Earth somehow, then we would know that FL is at least high enough for life to have appeared on 2 out of the very small number of potentially habitable worlds we've examined in detail. That would suggest FL might be relatively high, perhaps even close to 1, implying that most habitable worlds develop life given enough time. This wouldn't tell us anything about Fi or Fc, the factors related to intelligence and technology. K2-18b almost certainly doesn't host intelligent life. The environment seems too hostile for complex organisms to evolve, let alone civilizations capable of building radio telescopes. But if simple life is common, then the galaxy might be full of microbe-covered worlds, with intelligence and technology being much rarer. Some researchers have proposed a modified version of the Drake equation for estimating the number of living but non-technological worlds. This version would drop the Fi and Fc terms and focus on the prevalence of any kind of life. Even if we're the only technological civilization in the galaxy, we might share the Milky Way with billions of worlds hosting microbial biospheres, invisible to us except through the atmospheric biosignatures we're learning to detect. The Drake equation was always meant to be refined as our knowledge improved. Drake himself emphasized that it was a way of organizing our ignorance, identifying which questions we needed to answer to understand our place in the cosmos. Each factor in the equation represents an active area of research, from planet formation to the origins of life to the evolution of intelligence. K2-18b addresses the F-L factor, but it also touches on N-E in an interesting way. If Hycean worlds can host life, then the number of potentially habitable environments per planetary system increases dramatically. We should count not just the rocky planets in the habitable zone, but also the sub-Neptunes that might maintain liquid water beneath hydrogen atmospheres. This expands the real estate available for life significantly. There's a philosophical dimension to the Drake equation worth contemplating. It's an optimistic framework, assuming that each factor is greater than zero, that life can arise, that intelligence can evolve, that civilizations can develop technology and persist long enough to be detectable. A pessimistic version might suggest that one or more of these factors is effectively zero, that we're alone not because life is rare but because intelligence is impossible, or civilizations are inherently self-destructive. K2, 18b can't answer those deeper questions about intelligence and civilization, but it can begin to address the most fundamental question: does life exist elsewhere? And if the answer is yes, even if it's just microbes in an alien ocean, then the Drake equation becomes more than a thought experiment. It becomes a tool for understanding a living galaxy, a cosmos where biology is woven into the fabric of reality, waiting to be discovered by those patient enough to look carefully at the light from distant stars. What counts as evidence for life beyond Earth? This question has occupied philosophers of science and astrobiologists for decades, and K2-18b brings it into sharp focus. The atmospheric signatures we detect are indirect, filtered through hundreds of trillions of miles of space, interpreted through models and statistical analyses. How certain do we need to be before we claim discovery? In science, different types of claims require different levels of evidence. Detecting a new element or a new particle requires rigorous standards, multiple independent confirmations. Ruling out experimental artifacts. Discovering a new species requires a specimen that can be examined and categorized. But discovering life on another world presents unique challenges because we can't collect a specimen, can't run controlled experiments, can only observe from a distance using light as our messenger. Atmospheric biosignatures represent what scientists call circumstantial evidence. We detect molecules that are consistent with biological activity. But we don't see the organisms themselves. We infer their presence from their effects on the environment. This is similar to how paleontologists infer ancient life from fossils, or how detectives infer crimes from physical evidence. The inference can be strong, compelling even, but it's not the same as direct observation. The scientific community has developed frameworks for evaluating biosignature claims. The most robust approach involves looking for combinations of gases that are difficult to explain through abiotic processes alone. On Earth, the presence of oxygen and methane together is a powerful biosignature because these gases react with each other and shouldn't coexist unless something continually replenishes them. On K2-18b, the combination of methane and dimethyl sulfide in the absence of ammonia creates a similar situation, a set of conditions that abiotic processes struggle to produce. But even combinations of gases aren't definitive proof. We've been surprised before by nature's creativity in producing complex chemistry without biology. Venus, for instance, has clouds containing sulfuric acid and other sulfur compounds that Earth-like models struggle to explain. Recent tentative detections of phosphine in Venus's atmosphere sparked debate about whether this could be a biosignature, with the controversy highlighting how difficult it is to rule out all possible abiotic explanations. The standard for claiming detection of life has to be high, perhaps unreasonably high, by the standards of other scientific fields. Carl Sagan famously said that extraordinary claims require extraordinary evidence. The claim that we've found life beyond Earth is certainly extraordinary. What level of evidence makes that claim credible? Some researchers have proposed a confidence scale for biosignature detections, ranging from tentative detections requiring follow-up to definitive discoveries that leave no reasonable doubt. K218b currently sits somewhere in the middle of this scale. The evidence is intriguing and statistically significant, but it's not yet definitive. The dimethyl sulfide needs confirmation. Alternative explanations need to be thoroughly investigated. Additional observations need to either strengthen or weaken the case. There's also the question of reproducibility. In laboratory science, an experiment should produce the same results when repeated by independent researchers. For K218b, reproducibility means repeated observations showing consistent atmospheric signatures over time. If the biosignatures appear in some datasets but not others, that would weaken the case significantly. Consistency across multiple observations using different instruments would strengthen it. The role of modelling is crucial in interpreting the evidence. We can't directly measure K218b's ocean or its hypothetical organisms. We build computer models that simulate the planet's atmosphere and chemistry, then compare those models to our observations. The models are only as good as our understanding of planetary science and chemistry. If we're missing some important process, our models might be wrong, leading us to misinterpret the data. This is why the scientific community approaches biosignature claims with healthy skepticism. Skepticism doesn't mean dismissing the evidence. It means demanding rigorous testing and being willing to consider alternative explanations. The scientists studying K218b are appropriately skeptical, even as they acknowledge that the evidence is compelling. They're doing the hard work of trying to prove themselves wrong, looking for ways the data could be explained without invoking biology. Eventually, if the evidence accumulates sufficiently, the burden of proof might shift. Instead of biologists needing to prove life exists on K2-18b, skeptics would need to explain how all the observations could arise without life. This is how scientific consensus forms. Through the gradual accumulation of evidence that makes one explanation overwhelmingly more probable than alternatives. We might never achieve absolute certainty about K218b unless we send a probe there to sample its ocean directly, and that won't happen anytime soon given the distance and our current technology. But absolute certainty isn't required for scientific conclusions. We operate with the best explanation that fits the available evidence, always ready to revise our understanding if new data demands it. The nature of evidence in astrobiology is that it will almost always be indirect, statistical, based on remote observations and modelling. We're learning to work within those constraints, to develop rigorous frameworks for evaluating claims. To communicate uncertainty honestly while still drawing meaningful conclusions, K2-18b is teaching us how to do this, how to navigate the space between wild speculation and unreasonable skepticism, how to make careful claims based on the evidence we have while acknowledging what we still don't know. Imagine for a moment what it might be like to be an organism in K2-18b's ocean. Not imagining consciousness or awareness, because these hypothetical microbes almost certainly lack both, but imagining the environment they inhabit, the pressures they face, the chemical gradients they exploit to extract energy from their surroundings. The ocean would be dark at depth, receiving little or no light from the red dwarf star above. The thick hydrogen atmosphere would scatter and absorb much of the incoming radiation before it reached the ocean surface. Life here wouldn't rely on photosynthesis, at least not in the deep ocean. Instead, organisms would harvest energy from chemical reactions, oxidizing or reducing various molecules dissolved in the water. The chemistry available would be different from Earth's oceans. Hydrogen would be abundant, dissolved from the atmosphere above. Methane might bubble up from deeper layers or from geological processes in the planet's interior. Carbon dioxide would be present, providing a carbon source for building organic molecules. Sulfur compounds would exist in various oxidation states, creating chemical gradients that life could exploit. On Earth, we have organisms that live in similar conditions. Bacteria and archaea that thrive in deep-sea hydrothermal vents or in underground aquifers far from sunlight. These organisms use chemosynthesis deriving energy from reactions involving hydrogen sulfide, methane, iron, or other chemicals. Some oxidize hydrogen gas, combining it with carbon dioxide to produce methane as a waste product. These methanogens, as they're called, are among the most ancient forms of life on Earth. Possibly similar to the very first organisms that arose in Earth's early oceans, K2-18b's organisms might resemble these chemotrophs, adapted to an environment rich in hydrogen and carbon. They might cluster around geological features where fresh chemicals well up from the planet's interior, or they might drift freely in the water, harvesting dissolved gases. They might form mats or biofilms at the interface between the ocean and atmosphere, where chemical gradients are steepest. The production of dimethyl sulfide, if it's real, suggests a sulfur metabolism. On Earth, phytoplankton produce DMS as they process dimethyl sulfoniopropanate, a sulfur-containing compound that helps them regulate their internal osmotic pressure. K2-18b's organisms might process sulfur for similar reasons, or for entirely different purposes related to their unique environment. The sulfur cycle on a Hycean world would be complex, with sulfur existing in multiple chemical forms and cycling between the ocean, atmosphere, and possibly the planet's interior. Reproduction would occur through simple cell division, each organism copying its genetic material and splitting into two daughter cells. There would be no sex, no complex life cycles, just endless division and occasional mutation creating variation for evolution to work with. Over millions or billions of years, these organisms might diversify into many species, each adapted to slightly different chemical niches within the ocean. The pressure in K2-18b's deep ocean would be immense, far greater than Earth's deepest trenches. Organisms would need cell membranes capable of maintaining integrity under these pressures, possibly using different lipids than Earth life employs. Their proteins would need to fold and function properly in high-pressure environments. Earth has organisms living at extreme pressures, so we know this is possible, but the specific adaptations would likely be different. Temperature would vary depending on depth and location. Near the ocean's surface, temperatures might be mild, similar to Earth's tropical waters. Deeper down, the temperature might increase due to pressure and internal heat from the planet's core. Some organisms might prefer the cooler surface regions, others the warmer depths, creating vertical stratification in the biosphere. One fascinating question is whether K2-18b's organisms would have DNA like Earth life, or some other form of genetic material. DNA is chemically stable and capable of storing vast amounts of information, which is why it evolved on Earth. But other molecules could potentially serve the same function. RNA is simpler than DNA and might be more primitive. Some researchers have proposed that early life might have used entirely different genetic molecules before settling on DNA and RNA, K2-18b's life. If it exists, it might use DNA by convergent evolution, or it might have independently evolved a different solution to the problem of heredity. There's something humbling about contemplating such alien life, organisms that share our fundamental nature as living things, but are adapted to conditions we can barely imagine. They would know nothing of Earth, nothing of sunlight or oxygen or dry land. Their entire existence would be bound to that hydrogen-wrapped ocean, beneath skies we would find toxic and oppressive, and yet they would be our cousins in the deepest sense, fellow travellers in the universe. Fellow experiments in what's possible, when chemistry becomes complex enough to self-replicate and evolve. If we could somehow communicate the nature of our world to them, if they had consciousness to comprehend it, what would they make of a planet where the atmosphere is thin and transparent, where deadly oxygen dissolves in the water, where organisms emerge from the ocean to live on dry land beneath an open sky? Our world would seem as alien to them as theirs does to us, and perhaps in that mutual alienness there's a kind of symmetry, a reminder that life adapts to its circumstances and that home is wherever chemistry has learned to resist entropy. The Fermi Paradox, named after physicist Enrico Fermi, asks a simple but profound question. If the universe is so vast and life is possible, where is everyone? The galaxy is billions of years old and contains hundreds of billions of stars. If life were common and intelligence eventually evolved, we should see evidence of technological civilizations everywhere, and yet we see nothing. No radio signals, no megastructures, no evidence of cosmic engineering. The silence is deafening. Many solutions to the Fermi Paradox have been proposed. Perhaps intelligent life is extraordinarily rare. Perhaps civilizations inevitably destroy themselves before achieving interstellar communication. Perhaps they exist but are deliberately hiding from us. Perhaps we're looking in the wrong places or in the wrong ways. Perhaps the universe is teeming with life, but technology and intelligence are so rare that we're effectively alone. K2-18b, if it hosts life, doesn't resolve the Fermi Paradox, but it does inform our thinking about it. If Hycean worlds commonly harbour microbial life, then the galaxy might be full of living planets, while still containing few or no technological civilizations. Life and intelligence might not be as tightly coupled as we once assumed. On Earth, life appeared relatively quickly in our planet's history, within a few 100 million years after the surface cooled enough to support liquid water. But complex multicellular life took billions of years longer to evolve. And intelligence, in the form of tool-using, language-capable species, appeared only in the last few million years, a tiny fraction of Earth's history. This suggests that the step from non-life to simple life might be relatively easy, while the steps from simple life to complex life and from complex life to intelligence are much harder. If this pattern is universal, then we should expect many worlds hosting microbes, but very few hosting anything more complex. The galaxy could be a microbe garden, abundant with simple life, but barren of minds capable of contemplating their place in the cosmos. Hycean worlds might be particularly poor environments for complex life to evolve. The high-pressure, hydrogen-rich conditions seem conducive to chemotrophic microbes, but hostile to the kind of multicellular organisms that require more structured environments. On Earth, complex life evolved in relatively shallow, well-oxygenated waters, where energy was abundant and selective pressures favoured increasing size and complexity. A deep Hycean ocean might lack the environmental conditions that drive such evolution. If K2-18b has life, it's probably been there for a long time, possibly billions of years, remaining microbial throughout its entire history. The organisms might be diverse, filling various chemical niches, but they're probably not building structures or developing nervous systems or wondering about the universe. They're just living, reproducing, evolving slowly in response to their unchanging environment. This scenario, a galaxy full of microbial life but devoid of intelligence, would be both disappointing and fascinating. Disappointing because it would mean we might never find peers to communicate with, other minds to share knowledge and perspective with across the stars. Fascinating because it would reveal life to be a common cosmic phenomenon, while simultaneously underscoring how unusual intelligence might be. There's a version of the Fermi Paradox specifically for biosignatures rather than technosignatures. If life is common and produces atmospheric signatures we can detect, why haven't we found them already? The answer is that we've only recently developed the technology to look. The James Webb Space Telescope represents humanity's first real capability to characterize exoplanet atmospheres in enough detail to detect biosignatures. We've examined only a handful of potentially habitable worlds so far. K2-18b might be the first of many discoveries, or it might be unusual in ways we don't yet understand. Some researchers have proposed what they call the _0_some step in the evolution from non-life to spacefaring civilization that's extraordinarily difficult to pass. The filter could be behind us, the step from non-life to life, which would explain why Earth exists but suggest we're alone. Or it could be ahead of us, perhaps in the transition from single-planet civilization to interstellar expansion, which would suggest our future is precarious. If K2-18b confirms that the step from non-life to life is relatively easy, That would suggest the great filter is ahead. Somewhere in the journey from microbes to intelligence to technology to interstellar civilization, this would be ominous in one sense, implying that our survival and expansion are not guaranteed, but it would also be hopeful, showing that we've already passed the first and perhaps most crucial hurdle, that we exist as a thinking species at all. The silence of the cosmos takes on different emotional tones depending on how we interpret it. If we're truly alone, the silence is both terrifying and precious, emphasizing the unique value of Earth's biosphere and the immense responsibility we bear as the universe's only witnesses to itself. If we're surrounded by microbial life but no intelligence, the silence is less absolute but still profound, a reminder that awareness itself might be the rarest thing in existence. And if intelligence is common but civilizations are short-lived or non-communicative, the silence becomes a warning, a reminder that survival requires wisdom and restraint, and a willingness to overcome the challenges that face any technological species. K218b can't tell us which interpretation is correct, but it can begin to narrow the possibilities, and in doing so, it helps us understand both the cosmos and ourselves a little better, and perhaps that understanding brings its own quiet comfort. Humanity's search for life beyond Earth has a long and fascinating history, stretching back centuries before we had the technology to conduct meaningful searches. The question of whether we're alone has occupied philosophers, theologians, and scientists across cultures and throughout time, reflecting something fundamental about human curiosity and our need to understand our place in the cosmos. The ancient Greeks debated the possibility of other worlds. Epicurus, in the 3rd century BCE, argued that the infinite universe must contain countless other worlds, some likely inhabited. Aristotle disagreed, claiming Earth was unique and central, surrounded by perfect celestial spheres. These debates continued through the Middle Ages, where theological concerns often dominated discussions of life beyond Earth. The invention of the telescope in the early 1600s transformed speculation into observation. Galileo's discoveries of mountains on the Moon and moons orbiting Jupiter showed that celestial bodies were worlds in their own right, not perfect ethereal spheres. This opened the possibility that they might harbour life. Astronomers began searching for signs of lunar inhabitants or Martian civilizations, interpreting ambiguous observations as evidence for what they hoped to find. By the late 1800s, the search for life focused primarily on Mars. Astronomer Percival Lowell famously mapped what he believed were canals on Mars, artificial waterways built by an advanced Martian civilization struggling to transport water from the poles to equatorial regions. Lowell's maps were detailed and his arguments passionate, but improved telescopes revealed the canals to be optical illusions, patterns the human mind imposed on random features. The development of radio astronomy in the mid-20th century opened new possibilities. Radio waves could travel vast distances through space, and if technological civilizations existed, they might emit detectable radio signals either deliberately or as leakage from their communications. The search for extraterrestrial intelligence, or SETI, began in 1960 when astronomer Frank Drake pointed a radio telescope at 2 nearby sun-like stars, listening for artificial signals. He heard nothing, but the search has continued intermittently for over 60 years. SETI searches have scanned millions of stars across many wavelengths, looking for narrowband signals or repeated patterns that would indicate artificial origin. The searches have found nothing convincing, though there have been intriguing false alarms. The famous quote, "one signal detected in 1977, remains unexplained but is never repeated. Most SETI scientists believe technological civilizations, if they exist, must be rare or communicate in ways we haven't anticipated. Parallel to SETI, planetary scientists began exploring the solar system with robotic probes. The Mariner missions to Mars in the 1960s and 70s revealed a cold, dry world with a thin atmosphere, nothing like the habitable planet Lowell had imagined. The Viking landers in 1976 conducted experiments designed to detect Martian microbes, with ambiguous results that most scientists interpret as negative, though debate continues. The discovery of extremophils on Earth, organisms thriving in environments previously thought too hostile for life, expanded the range of conditions considered habitable. Scientists found bacteria living in boiling hot springs, in frozen Antarctic lakes, in acidic mine drainage, in rocks miles underground. These discoveries suggested that life was more resilient and adaptable than we'd imagined, raising the possibility that Mars or the ice-covered moons of Jupiter and Saturn might harbour life in subsurface oceans or underground aquifers. The 1995 discovery of the first 90 minutes. You've been here for 90 minutes, quietly, patiently, choosing this over everything else the world was offering you tonight. Do you know how rare that is? Most people cannot sit with something slow and meaningful for more than a few minutes before reaching for something louder. But not you. Not tonight. This channel exists for exactly this kind of person, and a like and subscribe is how we find more of them. It is how we find each other. Thank you for still being here. Now let's continue. The 1995 discovery of the first exoplanet around a sun-like star, 51 Pegasi b, transformed the search yet again. If other stars had planets, then the number of potential habitable environments in the galaxy might be vast. The Kepler Space Telescope, launched in 2009, discovered thousands of exoplanets and showed that planetary systems are the norm rather than the exception. But finding planets and characterizing them are different challenges. Most exoplanets discovered by Kepler are too far away for detailed atmospheric studies with current technology. The development of the James Webb Space Telescope and other advanced instruments finally gave astronomers the tools to study exoplanet atmospheres in detail, to search for biosignatures across light years of space. K2-18b represents the culmination of this long history, the latest chapter in humanity's search for life beyond Earth. Where Lowell saw canals on Mars through wishful thinking and limited optics, we see methane and dimethyl sulfide in a distant atmosphere through sophisticated spectroscopy and careful analysis. Where Drake listened for radio signals from putative civilizations, we search for the chemical signatures of simple organisms going about their existence. The methods have changed, becoming more rigorous and more technically sophisticated, but the fundamental question remains the same. Are we alone? The fact that we still don't know the answer, despite centuries of searching, tells us something about the nature of the question and the vastness of the space we're searching. But the progress we've made, the tools we've developed, the knowledge we've accumulated, suggests that we're finally approaching the point where we might find an answer, and K2-18b might be where that answer begins to emerge. K2-18b is not the only world where scientists have searched for signs of life. The solar system contains several promising candidates, and exoplanet surveys have identified numerous potentially habitable worlds. Understanding where K2-18b fits in this broader context helps us appreciate both its significance and its limitations. Within our own solar system, Mars remains a primary target. Despite the disappointment of finding it cold and dry, Mars almost certainly had liquid water on its surface billions of years ago. Ancient river valleys, lake beds, and mineral deposits paint a picture of a warmer, wetter past. If life arose on early Mars, some organisms might persist in underground aquifers or frozen in permafrost, waiting to be discovered by future rovers or sample return missions. Europa, one of Jupiter's large moons, is covered in ice, but appears to have a global ocean beneath its frozen crust. The ice is constantly being broken and reformed, creating a young surface with few impact craters. Plumes of water vapour have been detected erupting from Europa's surface, suggesting the ocean beneath is in contact with the ice above. This ocean might contain life, organisms living around hydrothermal vents similar to those in Earth's deep oceans, where chemotrophic bacteria thrive. Enceladus, a small moon of Saturn, definitely has a subsurface ocean. The Cassini spacecraft flew through plumes of water vapor and ice erupting from cracks in Enceladus's south polar region, analysing their composition. The plumes contained salt, organic molecules and hydrogen gas, all ingredients that could support life. Future missions might sample these plumes directly, searching for biosignatures without needing to land on the moon's surface. Titan, Saturn's largest moon, is another intriguing candidate, though in a very different way. Titan has a thick nitrogen atmosphere and liquid methane lakes and rivers on its surface. It's far too cold for liquid water, but some scientists have speculated that life might exist using liquid methane as a solvent instead of water, with entirely different biochemistry than Earth organisms. This remains highly speculative, but Titan's complex organic chemistry makes it worth studying. Among exoplanets, several systems have attracted particular attention. The TRAPPIST-1 system contains 7 Earth-sized planets, orbiting a small red dwarf star 40 light-years away. 3 of these planets orbit in the habitable zone, and future observations might reveal whether they have atmospheres and whether those atmospheres show biosignatures. The system's proximity and the number of potentially habitable worlds make it a priority target for characterization. Proxima Centauri b, the closest known exoplanet at just over 4 light-years away, orbits in its star's habitable zone. However, Proxima Centauri is an extremely active red dwarf, producing frequent and powerful flares. Whether a planet could maintain an atmosphere and liquid water under such bombardment remains uncertain. Future observations will help determine if Proxima b is truly habitable, or if it's a barren radiation-scorched rock. LHS 1140b is a super-Earth orbiting a red dwarf 48 light-years away. It's more massive than Earth, but receives less radiation from its star, possibly making it a water world covered entirely by deep oceans. Spectroscopic observations might reveal whether it has a water-rich atmosphere and possibly biosignatures. Some models suggest it could be another Hycean world, similar to K2-18b, but cooler and denser. TOI-700d is an Earth-sized planet orbiting in the habitable zone of a red dwarf 100 light-years away. Models suggest it might have a thick carbon dioxide atmosphere with oceans on the surface, possibly similar to early Earth before oxygen accumulated. It's far enough that detailed characterization will be challenging with current instruments, but future telescopes might reveal its secrets. Among these candidates, K218b stands out because we already have spectroscopic data showing complex atmospheric chemistry. We're not just hoping it might be habitable, we have evidence suggesting it actually could be harbouring life right now. Most other exoplanet candidates are still at the stage of being potentially habitable based on their size and orbit, without detailed atmospheric characterization. The search for life has become a multi-pronged effort, looking in many places using many techniques. Sample return missions to Mars and the moons of the outer solar system might bring back material that can be analysed in laboratories on Earth with far greater sensitivity than spacecraft instruments allow. Atmospheric characterization of exoplanets will continue to improve as newer, more powerful telescopes come online. Each approach has strengths and limitations. K218b will likely never be visited by spacecraft, at least not with any technology we can envision developing in the next few centuries. 26 light-years is too far for chemical rockets, and even advanced propulsion concepts would take decades or centuries to make the journey. Our knowledge of K218b will come entirely from remote observations, from analysing the light that reaches us across the void. But those observations can be remarkably revealing. We can determine the atmospheric composition, temperature structure, weather patterns, and possibly detect biosignatures, all without ever going there. This is both the limitation and the power of astronomy, the ability to reach across impossible distances with light as our only messenger, extracting information from photons that have travelled for decades to reach our instruments, and in doing so, connecting with worlds we'll never touch. The James Webb Space Telescope represents the current state of the art in space-based astronomy. but it's not the end of the development of our observational capabilities. Future missions already in planning or under development will push our ability to characterize exoplanet atmospheres even further, potentially resolving lingering questions about K2-18b and discovering biosignatures on other worlds. Webb's successor in many ways is already being conceived. NASA is studying concepts for what it calls the Habitable Worlds Observatory, a space telescope specifically designed to search for life on potentially habitable exoplanets. This observatory would have a larger mirror than Webb, possibly 8 to 12 meters in diameter, and would be optimized for detecting atmospheric oxygen, ozone, methane, and other biosignatures on rocky planets in the habitable zones of Sun-like stars. The challenge with rocky planets is that they're smaller than sub-Neptunes and their atmospheres are thinner, making biosignatures harder to detect. They also tend to orbit Sun-like stars rather than red dwarfs, meaning they're farther from their stars and harder to observe during transits. The Habitable Worlds Observatory would address these challenges with increased sensitivity and specialized instruments. Another approach is to use a star shade, a giant flower-shaped screen that flies in formation with a space telescope, blocking the light from a star to allow direct observation of its planets. Current telescopes observe planets through transits, catching the faint shadow as they pass in front of their star. A star shade would enable direct imaging, allowing us to see the planet's reflected light without being overwhelmed by the star's glare. This would open up new types of observations, including looking for seasonal changes that might indicate biological activity. Ground-based telescopes are also getting dramatically larger. The extremely large telescope under construction in Chile will have a main mirror 39 meters across, composed of hundreds of segments that work together like Webb's hexagonal mirrors, but on a much larger scale. While ground-based telescopes must contend with Earth's atmosphere, which absorbs infrared light and creates turbulence that blurs images, they benefit from their enormous size and the ability to upgrade instruments without launching new missions. Adaptive optic systems can compensate for atmospheric turbulence by rapidly adjusting mirrors to counteract the blurring effects of air. The most advanced systems use lasers to create artificial guide stars in the upper atmosphere, measuring the distortion and correcting for it in real time. These technologies allow ground-based telescopes to achieve resolution comparable to space telescopes for certain observations. Radio telescopes continue to advance as well, particularly arrays that combine signals from multiple dishes to create the equivalent of a much larger telescope. The square-kilometre array, currently under construction in South Africa and Australia, will be the most sensitive radio telescope ever built, capable of detecting extremely faint signals from distant galaxies and possibly from technological civilizations if they exist and are transmitting. For characterizing planets like K2-18b, the key advancement will be in spectroscopic resolution and sensitivity. Higher resolution spectrographs can separate closely spaced spectral lines, revealing more detail about atmospheric chemistry. Greater sensitivity allows detection of molecules present in smaller concentrations. Both improvements will help confirm or refute the tentative dimethyl sulfide detection on K2-18b and search for additional biosignatures. Another important development is in computer modelling. As our computational power increases, we can run more sophisticated models of planetary atmospheres, accounting for more variables and exploring parameter space more thoroughly. Machine learning algorithms are being developed to analyze spectroscopic data, potentially identifying patterns that humans might miss. These tools will help us interpret the increasingly complex data sets that future telescopes will provide. Time is also a factor. Webb can only observe so many targets in its lifetime. Each observation requires careful planning and uses precious telescope time that's competed for by astronomers worldwide. Future dedicated missions for exoplanet characterization will spend most or all of their time on this one scientific goal, allowing more thorough study of interesting candidates like K2-18b. Sample return missions while not feasible for exoplanets, remain possible for solar system targets. Bringing back material from Mars, Europa, or Enceladus for analysis on Earth would allow far more detailed study than remote observations permit. We could look for fossil biosignatures, analyse organic chemistry with laboratory instruments, search for metabolic processes or genetic material. A single sample containing actual evidence of life would be worth more than decades of remote spectroscopy. The technology we need to definitively answer questions about K218b and other potentially habitable worlds is coming, but it will arrive on the timescale of decades rather than years. Space missions take time to plan, develop, and launch. Telescopes take years to build, but the progress is real and accelerating. Each new instrument builds on lessons learned from its predecessors. Each observation of K218b informs what observations we should make next. In the meantime, we work with what we have, pushing current instruments to their limits, developing new analysis techniques, refining our models. The patient work of science continues, and with each advance we come closer to understanding not just K2-18b, but the broader question of life's prevalence in the universe, and whether we're truly alone or part of a living cosmos. Understanding what makes a planet habitable requires understanding the requirements for life itself. While we only have one example to study in detail, Earth's biosphere has taught us much about what living systems need to function and persist over billions of years. At the most fundamental level, life requires energy, raw materials, and liquid solvent. Energy drives the chemical reactions that maintain organization against entropy. Raw materials, particularly carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, provide the building blocks for complex molecules. A liquid solvent, usually water, allows molecules to move and interact, enabling the chemistry of life. Earth's organisms get energy from various sources. Photosynthesis captures energy from sunlight, using it to build sugar molecules from carbon dioxide and water. Chemosynthesis extracts energy from chemical reactions, oxidizing or reducing molecules like hydrogen sulfide, methane, or iron compounds. Some organisms derive energy from the radioactive decay of elements in rocks. The diversity of energy sources life has learned to exploit suggests that energy availability, rather than a specific energy source, is what matters. Water serves as life's solvent because of its unique chemical properties. It's a polar molecule, meaning it has slightly positive and negative ends, allowing it to dissolve many different compounds. It remains liquid over a wide temperature range at pressures found on planetary surfaces. It's abundant in the universe, formed from the two most common elements, hydrogen and oxygen. While some scientists have speculated about life using other solvents like methane or ammonia, water remains the most likely medium for biology. Beyond these basic requirements, habitable planets need stability. Life takes time to evolve, requiring environments that remain hospitable for millions or billions of years. A planet in an unstable orbit, or around a star that varies wildly in output, might not provide the steady conditions needed for life to establish itself. Earth has maintained liquid water on its surface for at least 3.8 billion years, possibly longer, giving life ample time to arise and diversify. Protection from radiation is important, particularly for complex life. Earth's magnetic field deflects much of the solar wind, preventing it from stripping away our atmosphere. Our ozone layer absorbs ultraviolet radiation that would otherwise damage DNA and other biological molecules. Planets without these protections might still harbour life, but would be limited to underground or underwater environments, where the overlying rock or water provides shielding. The composition of a planet's atmosphere affects habitability in complex ways. Too thick an atmosphere creates crushing surface pressures and greenhouse heating. Too thin an atmosphere can't maintain liquid water, which evaporates or freezes depending on temperature. The right balance depends on the distance from the star and the star's energy output. K218b's thick hydrogen atmosphere might seem hostile, but it could maintain a habitable environment at the ocean surface through the greenhouse effect while providing radiation protection. Plate tectonics, the slow churning of a planet's crust, might be important for long-term habitability. On Earth, plate tectonics recycles carbon between the atmosphere and interior, regulating the greenhouse effect and maintaining stable temperatures over geological time. Planets without plate tectonics might see their atmospheres either run away into a hothouse or freeze out entirely. However, this requirement is debated. And alternative carbon cycles might maintain stability. Chemical cycling between different reservoirs, atmosphere, ocean, interior, is probably essential for maintaining habitable conditions. On Earth, the carbon cycle moves carbon between air, water, rock, and life. The nitrogen cycle does the same for nitrogen. These cycles prevent the atmosphere from drifting into uninhabitable states. K218b, if it has biology, would have its own chemical cycles involving hydrogen, methane, carbon dioxide, and sulfur compounds, with life participating in and possibly regulating those cycles. The concept of a habitable zone, the range of distances from a star where temperatures allow liquid water, is useful but oversimplified. The actual habitability of a planet depends on many factors beyond distance: atmospheric composition, greenhouse effect, internal heat, tidal heating from nearby planets or moons, reflectivity of the surface, and more. Some worlds outside the traditional habitable zone, like Europa or Enceladus, might be habitable due to tidal heating. Some worlds inside it, like Venus, are hellish, despite being at roughly the right distance from the Sun. Hycean worlds expand our concept of habitability significantly. Instead of requiring rocky planets with thin atmospheres, we can include sub-Neptunes with hydrogen envelopes and water oceans. This dramatically increases the number of potentially habitable environments in the galaxy. The requirements shift from quote 2 to simply quote 3, which many different types of worlds might achieve. K2-18b appears to meet the fundamental requirements for life. It has liquid water, or at least conditions where liquid water should exist. It has energy available in the form of chemical gradients between different molecules in its atmosphere and ocean. It has raw materials including carbon, hydrogen, oxygen, nitrogen, and sulfur. It's in a stable orbit around a long-lived star. If these factors are sufficient, life should be possible there. Whether life is actually present depends on the probability that chemistry makes the leap to self-replication and evolution. On Earth, this happened relatively quickly after the planet cooled enough to support life, suggesting the transition might not be terribly improbable. But we have only one data point, and it's dangerous to generalize from a sample size of 1. K2-18b could provide that crucial second data point, allowing us to begin understanding what it truly takes for life to arise, and whether the universe is fundamentally fertile or fundamentally barren. The possibility of detecting life on K2-18b raises philosophical questions that humanity has contemplated for centuries, but never had to address practically. What would it mean to know life exists elsewhere? How would this knowledge change us? What responsibilities would it create? First, there's the question of value. Does life have intrinsic worth, regardless of whether it's intelligent or aware? Most ethical frameworks developed on Earth focus on sentient beings capable of experiencing pleasure and pain, or on rational beings capable of making moral choices. Microbes presumably have no experiences, no awareness, no capacity for suffering or joy, yet they would be alive, participating in the same fundamental process of self-replication and evolution that connects all Earth's organisms. If we value life for its own sake, then discovering it on K2-18b would immediately create obligations. We would have a responsibility to protect that biosphere, to avoid contaminating or disrupting it. This might seem academic given that we have no ability to travel to K2-18b, but it sets a precedent for how we approach other worlds we can reach, like Mars or Europa. The concept of planetary protection already guides our exploration of the solar system. Spacecraft sent to Mars or the moons of Jupiter are carefully sterilized to avoid introducing Earth organisms that might contaminate potential habitats. The protocols balance scientific interest in finding life against the need to preserve pristine environments. If we confirm life on K2-18b, it would strengthen arguments for strict planetary protection on other worlds we study. There's also the question of whether we should attempt to communicate with K2-18b's biosphere, not in the sense of sending messages to microbes, which would be pointless, but in the sense of whether we should deliberately send probes or signals toward the planet. Some argue that any life-bearing world should be left completely alone, a wilderness preserve on a cosmic scale. Others contend that careful study, even if it requires physical presence, would be justified by the knowledge gained. This touches on a deeper question about humanity's role in the cosmos. Are we observers, cataloguing and studying but never interfering? Are we gardeners, with a responsibility to nurture and protect life wherever we find it? Are we explorers, with a right to go anywhere our technology permits? Different philosophical traditions give different answers, and discovering life on K2-18b would force us to choose among them. The detection of life beyond Earth would also affect how we think about our own significance. For thousands of years, humans have seen themselves as central to creation, either literally placed at the centre of the cosmos by divine will, or figuratively as the universe's only witnesses, the only beings capable of understanding and appreciating existence. Learning that we share the universe with other living things would diminish that centrality, placing us in a larger context. Some would find this humbling revelation disturbing, a blow to human dignity and importance. Others would find it liberating, a relief from the burden of cosmic loneliness and proof that we're part of something larger than ourselves. Both reactions are valid, reflecting different temperaments and worldviews. What matters is that we would be forced to update our self-understanding in light of new knowledge. Always a difficult but necessary process. There are also questions about how different cultures and religions would interpret the discovery. Some theological frameworks have already contemplated the possibility of extraterrestrial life and incorporated it into their understanding of creation. Others might find it challenging to reconcile with doctrines developed in eras when Earth was thought to be unique. The diversity of human responses to K2-18b's life would likely reflect the diversity of human thought about our place in the cosmos. The practical implications might be subtle. K2-18b is 26 light-years away, impossibly remote by current technology. Its organisms, if they exist, are microbes without culture or technology. There would be no communication, no exchange of ideas, no commerce or diplomacy. The impact would be entirely philosophical and scientific, changing how we think, but not how we live our daily lives. Yet perhaps that's enough. Humans have always cared about questions that have no practical importance. Questions about origins and meaning and our place in the larger scheme of things. We build telescopes and launch space probes not because they improve our material conditions, though sometimes they do, but because we want to know. The discovery of life on K2-18b would satisfy that wanting in the most profound way possible. Answering a question as old as consciousness itself. And there would be hope in the discovery, hope that life is resilient and creative, that it emerges wherever conditions allow, that the universe is fundamentally hospitable to the complex chemistry of living systems. In an age often characterized by anxiety about the future, about climate change and technological risk and the fragility of civilization, finding life flourishing in an alien ocean would remind us that biology is robust, that it persists through changes and challenges, that it adapts and endures. K2-18b cannot love us or know us. Its organisms, if they exist, will never contemplate the stars or wonder about Earth. But life calls to life across the distances, and in finding them, we would find a reflection of ourselves, not in form or thought, but in that fundamental drive to persist, to grow, to turn the raw materials of the cosmos into something organised and purposeful and alive. And perhaps that would be connection enough. Let's return for a moment to the concrete data, grounding ourselves in what the observations actually show before we drift too far into implications and philosophy. The spectra from K218b contain specific measurable features, absorption lines at particular wavelengths, each one telling a story written in the language of photons and molecules. The methane signature appears at wavelengths around 3.3 micrometers in the infrared spectrum, where methane molecules absorb light due to the vibrations of their carbon-hydrogen bonds. The signal is strong, unambiguous, appearing consistently across multiple observations. Comparing the strength of this absorption to models tells us approximately how much methane exists in K218b's atmosphere, something like 0.5 to 1% by volume, a significant amount compared to trace gases but much less than the dominant hydrogen and helium. Carbon dioxide shows up at different wavelengths, around 4.3 micrometers and 15 micrometers, where the carbon-oxygen bonds in CO2 absorb infrared radiation. Like methane, the carbon dioxide detection is robust and repeatable. The amount is harder to pin down precisely, but models suggest somewhere around 0.1 to 0.5%. Again, a substantial component of the atmosphere, though not dominant. The absence of ammonia is revealed by the lack of absorption features where ammonia should appear if it were present in significant quantities. Ammonia has characteristic absorption bands around 2 micrometers and 10 micrometers. The fact that these features are not seen in K218b's spectrum, despite the presence of hydrogen and nitrogen that should combine to form ammonia in a reducing atmosphere, is what makes the non-detection scientifically interesting. The tentative dimethyl sulfide feature appears around 9.5 micrometers, in a region of the spectrum where sulfur-containing molecules absorb light. The challenge with this detection is that the signal is weak, close to the noise level in the data, and other molecules can absorb at similar wavelengths. The statistical analysis suggests it's probably real, with a confidence level of about 95%, but this is below the traditional threshold for claiming a definitive detection in astronomy, which typically requires 99.7% confidence or higher. What makes the DMS signal compelling despite its weakness is the context. Finding it alongside methane and carbon dioxide in the absence of ammonia creates a pattern that's difficult to explain without invoking either very specific abiotic chemistry or biological activity. The probability calculations that yield the 99.7% likelihood of life don't come from the DMS detection alone, but from the combination of all the atmospheric features together. The temperature structure of K218b's atmosphere can be inferred from how absorption features vary across different wavelengths. Cooler regions of the atmosphere affect different wavelengths than hotter regions, allowing astronomers to build up a vertical temperature profile. The data suggests temperatures ranging from around 200 Kelvin or minus 73 Celsius in the upper atmosphere to possibly 300 Kelvin or 27 Celsius near the ocean surface, warm enough for liquid water to exist comfortably. The pressure at the ocean surface is harder to determine, but can be estimated from models of the planet's mass, radius, and atmospheric composition. Estimates suggest pressures somewhere between 10 and 100 times Earth's sea level pressure, substantial but not extreme by the standards of Earth's deep oceans or the surfaces of Venus. Organisms adapted to these pressures would find them normal. Just as deep-sea organisms on Earth thrive at pressures that would crush surface-dwelling creatures. One fascinating aspect of the data is what it doesn't show. There's no sign of oxygen, which we wouldn't expect in a hydrogen-rich atmosphere. There's no sign of phosphine, which had been tentatively detected in Venus's atmosphere and sparked controversy. There's no sign of industrial pollutants or other technosignatures, confirming that K218b, if inhabited, hosts only simple life. The precision of these measurements is remarkable, when you consider the challenges involved. The planet itself doesn't emit much light. What we detect is starlight filtered through its atmosphere during the few hours of each 33-day orbit when the planet transits its star. The atmosphere is hundreds of kilometers thick, but the light passes through only a thin annulus at the limb of the planet, the very edge where starlight grazes the atmosphere. The total change in the star's brightness due to the planet's atmosphere is measured in parts per million. Detecting specific molecular absorption features requires isolating changes of just a few parts per 100 million against the much larger signal from the star itself. This is like trying to detect the shadow of a gnat on a searchlight from 1,000 miles away, and yet Webb's instruments can do it, can extract meaningful spectral information from these infinitesimal signals. The error bars on each measurement tell their own story. Some features are measured with precision to within a few percent. Others, like the DMS signal, have uncertainties of 50% or more, reflecting the difficulty of extracting signal from noise at these faint levels. Future observations will reduce these uncertainties, either confirming features that are currently tentative or revealing them to be statistical flukes. What the numbers tell us ultimately is that K218b is a world with a complex atmosphere that doesn't fit simple models. It's not a straightforward hydrogen-helium envelope like most sub-Neptunes. It's not a rocky planet with a thin atmosphere like Earth. It's something in between, something new, a Hycean world that challenges our categories and invites deeper study, and the numbers, precise and impersonal, point towards something that might be alive. Close your eyes for a moment and try to picture it. An ocean beneath a hydrogen sky. Waves moving under the influence of tides raised by the red dwarf star overhead. Water that has never known sunlight as we understand it, but is illuminated instead by the deep crimson glow of a star cooler than any flame. The sky would be strange to eyes evolved under Earth's yellow sun. Hydrogen scatters light differently than nitrogen and oxygen, potentially creating atmospheric phenomena unlike anything we've witnessed. There might be clouds, water vapour condensing and forming droplets that fall as rain before evaporating and rising again. Or perhaps the atmosphere is too stable, too well mixed, for clouds to form in the way Earth's weather systems work. If you could somehow stand at the surface of K218b's ocean, breathing apparatus notwithstanding, you would feel pressure, perhaps 10 or 20 or 50 times what you experience at Earth's sea level. The weight of all that hydrogen pressing down, creating an atmosphere measured in hundreds of kilometres thick rather than the 100 or so kilometres of Earth's much thinner air. The water itself might be warmer than you'd expect, not from sunlight, but from the greenhouse effect of all the hydrogen and methane trapping heat, and possibly from geothermal energy rising from the planet's interior. Thermal vents might dot the ocean floor, spewing heated water rich in dissolved minerals, creating chemical gradients that life could exploit for energy. In Earth's oceans, we find remarkable diversity at hydrothermal vents. Tube worms cluster around the openings, housing chemotrophic bacteria in their tissues. Crabs and fish congregate in the warm water, feeding on the bacteria and on each other. The vents create oases of life in the deep ocean, independent of the photosynthetic ecosystems that dominate in shallower, sunlit waters. K218b's ocean might host similar communities, though the organisms would be simpler, lacking the complex body plans that require billions of years to evolve. The interface between ocean and atmosphere would be active, with gases dissolving into the water and bubbling out again. Methane generated deep in the ocean, or in the planet's interior, would rise through the water column, eventually escaping into the atmosphere. Carbon dioxide from volcanic activity or from biological respiration would dissolve in the water, making it slightly acidic, though buffered by dissolved minerals. If dimethyl sulfide is truly being produced by organisms, the surface of the ocean might have a faint smell, similar to the sulphurous odour of tidal pools on Earth where bacteria process organic matter. Not unpleasant exactly, but distinct, a marker of biological activity transforming the chemistry of the environment. Deeper in the ocean, beyond where any light penetrates, the world would be dark and quiet and cold or warm depending on proximity to thermal vents. Pressure would increase with depth, eventually reaching the point where water transitions to ice despite the temperature, forming high-pressure ice phases that don't exist under normal conditions on Earth. These exotic ice layers might form the floor of the ocean, or there might be a rocky or metallic core beneath even those. The ocean's depth remains uncertain, potentially hundreds of kilometers from surface to solid interior. Far deeper than Earth's oceans, which average about 4 kilometers deep. In such a deep ocean, vertical stratification would be pronounced, with different temperatures and pressures and chemical compositions at different depths. Organisms might specialize for particular depth ranges, just as Earth's ocean life shows clear stratification from surface to abyssal zones. There would be no light zones in K218b's ocean, no shallow waters where photosynthesis could occur. Any organisms would depend entirely on chemical energy, creating ecosystems that function in perpetual darkness. On Earth, such ecosystems exist in caves and deep ocean trenches, proving that biology doesn't require sunlight. K2-18b would extend that principle to an entire planet, an entire biosphere built on chemosynthesis rather than photosynthesis. If the planet is tidally locked, one hemisphere would receive constant illumination from the star while the other faces eternal darkness. The ocean currents would transport heat from dayside to nightside, creating enormous circulation patterns. The terminator region, where day and night meet, might be the most dynamic environment, with temperature gradients driving convection and weather systems. But we will never see this ocean, never feel those waves, never sample that water, or witness those hypothetical organisms going about their existence. 26 light-years is an unbridgeable distance with any technology we can currently imagine. Even travelling at a tenth the speed of light, which would require propulsion systems far beyond anything we have built, the journey would take 260 years. So the ocean remains imaginary, constructed in our minds from spectral data and atmospheric models, as real as physics and chemistry say. It must be yet as remote as something existing only in dreams. We can picture it, wonder about it, dedicate our careers to studying it from afar, but we cannot touch it. Cannot confirm through direct observation that our models are correct and the water truly exists beneath that hydrogen envelope. And yet there's something profound in this limitation, this ability to know something exists yet being unable to reach it. It mirrors so many aspects of human experience, the things we understand intellectually but cannot experience directly, the places we know exist but will never visit, the questions we can answer in principle but not in practice. K218b's ocean, whether it hosts life or not, represents the vast majority of the universe, the parts we can see and study but never touch, and perhaps learning to find meaning in that distance is itself a form of wisdom. In the sweep of cosmic time, in the vastness of the universe with its 2 trillion galaxies, each containing hundreds of billions of stars, the question of whether microbes exist in one particular ocean, around one particular red dwarf, might seem small, and yet it matters enormously, not for what it changes in the universe, but for what it changes in us. For most of human history, we believed ourselves to be central, unique, the purpose for which everything else existed. The Earth sat unmoving at the centre of creation, with the sun, moon, planets and stars revolving around us in perfect celestial spheres. We were special, chosen, the focal point of divine attention and cosmic significance. This comfortable centrality has been progressively dismantled by science. Copernicus showed that Earth orbits the sun, not vice versa. Galileo revealed that other planets have moons, that celestial bodies are worlds in their own right. Herschel demonstrated that the sun is just one star among billions in a galaxy. Hubble showed that our galaxy is one among countless others, all rushing away from each other as space itself expands. Each discovery pushed us further from the centre, reduced our cosmic significance, revealed us to be inhabitants of an ordinary planet around an ordinary star in an ordinary galaxy in an apparently infinite universe. This progressive displacement has been called the Copernican principle, the idea that we occupy no special position in the cosmos, that our location and circumstances are typical rather than exceptional. Finding life on K2-18b would represent another step in this progression. Life itself would no longer be unique to Earth. Biology would be revealed as a general phenomenon of chemistry and physics, arising wherever conditions allow. We would be one living world among potentially billions, our biosphere typical rather than miraculous. Our existence explained by natural processes rather than requiring special creation. Some see this displacement as diminishing human worth, as reducing us to insignificance in an uncaring cosmos. If we're not special, if we're just one random instance of a common phenomenon, what meaning does our existence have? Why should we care about ourselves or each other? What value do we possess? Either way, the responsibility is ours. Whether we're alone or surrounded by microbial neighbours, we're the only beings in our neighbourhood with the power to choose, to act ethically, to take the long view, to care about things beyond our immediate survival. That power comes with responsibility, to ourselves, to other species on Earth, to future generations, and perhaps to the potential for life elsewhere that we might someday encounter. K2-18b can't tell us what we should do with this responsibility, but it can help us understand its scope and significance. And in a universe where so much remains uncertain, where we're constantly updating our understanding based on new evidence, perhaps that's enough, to know that we're asking the right questions and that each answer we find, however incomplete, brings us closer to understanding our place in the cosmos and what we owe to the gift of existence. Step back for a moment and consider the timescales involved in this story. The vast stretches of time that separate events and give context to our brief observations of K2-18b. The universe began 13.8 billion years ago in the event we call the Big Bang. Space itself expanded from an inconceivably hot, dense state, creating the fundamental particles that would eventually form atoms and molecules and stars and planets, and on at least one world and possibly many. Living organisms capable of contemplating their own origins. The first stars formed a few 100 million years after the Big Bang, massive and short-lived, producing the first heavy elements in their cores and scattering those elements through space when they exploded as supernovae. These elements, carbon and oxygen and nitrogen and iron and all the others, are the raw materials for planets and life, forged in stellar furnaces and distributed through the cosmos by stellar death. K2-18. The red dwarf star at the centre of our story formed much later, perhaps 6 or 7 or 8 billion years ago, when the galaxy had been enriched with heavy elements from countless generations of earlier stars. The cloud of gas and dust that collapsed to form K2-18 also formed a disk of material around the young star, and from that disk planets coalesced, including K2-18b. If K2-18b is 4 billion years old, roughly the same age as Earth, then it has existed for nearly a third of the universe's total history. If life arose there shortly after the planet formed, then that biosphere might be almost as old as Earth's. Billions of years of evolution and adaptation producing organisms refined by natural selection over geological epochs. All of this happened before humans existed, before Earth had multicellular life, before our Sun even formed if K2-18 is among the older stars in our neighbourhood. The light we see from K2-18 today left that star 26 years ago, carrying information about the planet's atmosphere as it existed in 1998. That atmosphere, and the ocean beneath it, had already been evolving for billions of years by that point. Against these vast timescales, our observations represent an instant, a snapshot of a system that has been changing and evolving for eons. The organisms in K2-18b's ocean, if they exist, have no knowledge of our observation. They've been living their lives for billions of years without our awareness, and they'll continue long after we've finished studying them, indifferent to our telescopes and our speculations. This perspective is simultaneously humbling and liberating. Humbling because it emphasizes how brief our existence is compared to cosmic timescales, how recent our technological civilization is, how vanishingly small our individual lifespans are against the age of the universe. Liberating because it shows that the cosmos doesn't revolve around us, that it exists and functions according to laws that preceded our existence and will continue after we're gone. There's comfort in this long view, in recognizing that we're part of something much older and larger than ourselves. The atoms in our bodies were formed in ancient stars that died billions of years ago. The planet we live on will continue orbiting the sun for billions of years after human civilization has ended, whether through extinction or transcendence into something we cannot yet imagine. K218b2 has a long future ahead of it. Its star will continue burning for trillions of years, providing energy and stability for whatever life might have evolved there. The ocean will persist, cycling through geological and chemical processes on timescales measured in millions or billions of years. If organisms are there, they'll continue evolving, adapting to gradual changes in their environment, perhaps giving rise over unimaginable time to more complex forms we cannot predict. We're observing a moment in this planet's history, a brief window in its long existence. The atmospheric chemistry we detect is a snapshot of ongoing processes. Currents and cycles that have been operating for eons and will continue long after our last observation. This transience of our knowledge is worth acknowledging, a reminder that what we see is not permanent or complete, but partial and temporary. Yet even a moment can be precious. Even a snapshot can reveal truth. The fact that we're observing just one instant in K218b's long history doesn't make our observations meaningless. It makes them significant, a connection across time and space between our brief lives in this ancient world, a moment of understanding that bridges the void between us. The long view also provides perspective on the pace of discovery and understanding. 20 years ago, we didn't know if planets around other stars were common. 10 years ago, we couldn't characterize their atmospheres in detail. Today, we're debating whether we've detected signs of life on one of them. Where will we be in another 20 years? Another 50? What will we know about K218b and other worlds that we can barely imagine today? Science progresses on timescales much shorter than cosmic processes, but still longer than individual human lives. The work we do today builds on foundations laid by previous generations and will serve as foundations for discoveries made by future generations. We're part of a long conversation, a multi-generational effort to understand the cosmos, and K218b is one chapter in that ongoing story. In the longest view of all, from the perspective of billions of years hence when the sun has swollen into a red giant and Earth is uninhabitable. The question of whether K218b had microbial life in the early 21st century might seem trivial. But it won't be trivial to us living in this moment, asking these questions. The present is the only time we have, the only moment we can act in and understand. The fact that it's brief doesn't make it less important, and the knowledge we gain now, however incomplete, is genuine knowledge, hard-won understanding of how the universe works and where we fit within it. Light travels at the ultimate speed limit of the universe, 186,000 miles per second, the speed at which causality propagates through space. Nothing can go faster. This is written into the structure of space-time itself. And yet, even at this ultimate speed, light from K2-18 takes 26 years to reach Earth, crossing the vast emptiness between stars at the only speed the universe allows. Think about what this means. The photons that Webb's mirrors captured and focused into its spectrographs began their journey in 1998. They were emitted from the star K2-18, travelled through the planet's atmosphere during a transit, picking up the absorption signatures of methane and carbon dioxide and possibly dimethyl sulfide, and then continued outward into space. For 26 years, these photons travelled, crossing distances so vast that conventional units like miles or kilometres become meaningless. They pass through the emptiness between stars, through clouds of interstellar gas and dust, through regions of space where matter is so diffuse that you could travel for light years without encountering a single atom. They travelled through space that expanded as they moved, carrying them ever farther from their origin, stretching the distance between K2-18 and Earth, even as they bridged it. They passed other star systems, other planets, none of which noticed or cared about their passage. They were just photons, packets of electromagnetic energy, travelling at the speed of light because that's what light does. And then, after 26 years of travel, after crossing 150 trillion miles, they reached our solar system. They passed the outer planets, Jupiter and Saturn and Uranus and Neptune, bodies that dwarf our Earth yet are tiny compared to the distances between stars. They passed the orbit of Mars, crossed Earth's orbit, and continued outward to where Webb sits at L2, 1,000,000 miles beyond Earth, waiting with its golden mirrors pointed at the precise location in the sky where K2-18 would appear. The mirrors captured these photons, reflecting them down to the instruments that split them by wavelength and measured their intensity, creating the spectra that scientists would later analyse. And in those measurements, in the pattern of absorption lines, in the specific wavelengths where light was missing because molecules in K2-18b's atmosphere had absorbed it, we found evidence of that distant world's chemical composition. This is how we reach across the void, how we touch distant worlds we cannot visit. Light is our messenger, our only connection to the cosmos beyond our immediate neighbourhood. It carries information encoded in wavelength and intensity, information about temperature and composition and motion, information that we've learned to decode and interpret. Every observation we make of the universe is an observation of the past. The moon we see is the moon as it existed 1.3 seconds ago. The time light takes to travel from there to here. The sun we see is the sun as it existed 8 minutes ago. The nearest stars show us images from years in the past. K2-18 shows us what was happening there 26 years ago. Distant galaxies reveal the universe as it existed millions or billions of years ago, their light having travelled across vast cosmic expanses to reach us. We cannot see the present state of K2-18b. We can only see its past, and even that we see imperfectly. Sampling tiny fractions of the light that pass through its atmosphere during transits. The planet as it exists right now, at this moment, is unknowable to us. It won't become knowable for another 26 years, when light carrying information about the present moment completes its journey to Earth. This creates a strange relationship between us and the objects we study, a relationship mediated by time and distance, and the finite speed of light. We're observers of history, watchers of events that have already occurred, connected to the cosmos by photons that serve as messengers from the past. And yet this connection is real. The light is real, carrying genuine information about distant places. The molecules in K2-18b's atmosphere truly did absorb specific wavelengths, creating the patterns we detect. The chemistry we infer from those patterns represents actual processes occurring on that distant world. The distance doesn't make it less real, it just makes it remote, separated from us by space and time but connected by light. There's something poetic about this, about the patient travel of photons across the void, about the way information propagates through the universe at the speed of causality. Light connects everything, linking distant objects across space and time, allowing us to see and understand things we cannot touch. If there are organisms in K2-18b's ocean-producing dimethyl sulfide right now, we won't see evidence of that production for 26 years. If something catastrophic happened to the planet tomorrow, some event that stripped away its atmosphere or boiled its ocean, we wouldn't know for 26 years. The planet exists in two states for us. The observable past, which we can study and analyse, and the unknowable present, which we can only imagine and extrapolate from what we've seen. This is the fundamental limitation of astronomy, this reliance on light as our only messenger, this restriction to studying the universe as it was rather than as it is. And yet it's also astronomy's fundamental power, this ability to reach across impossible distances, to extract information from photons, to build understanding of worlds and galaxies and the universe itself using nothing but the light that reaches us. K218b sits there in the constellation Leo, orbiting its red dwarf star, potentially hosting life in its ocean, completely unaware of our observation. The organisms there, if they exist, don't know we exist. They cannot know. The information that we exist won't reach them for another 26 years, even if we deliberately sent a message at the speed of light. And they have no telescopes, no technology, no capacity for awareness beyond the simple stimulus response of bacterial metabolism. Yet we're connected anyway, by the light that travels between us, by the shared chemistry of life, by the fact that we're both products of the same physical laws operating in the same universe. The connection is tenuous, mediated by photons and mathematics and human curiosity, but it's real. And in recognizing it, in taking the time to observe and analyze and understand, we're participating in something larger than ourselves, reaching across the void to touch, however lightly, another world. We've travelled together for 2.5 hours now, drifting slowly through the story of K2-18b, this remarkable world orbiting a red dwarf star in the constellation Leo, 26 light-years from Earth. Thank you for staying with me through this entire journey, for giving your time and attention to this exploration of what might be one of the most significant discoveries in the history of astronomy. From the initial detection of this planet by the Kepler telescope, to the remarkable observations made by the James Webb Space Telescope, from the tentative evidence of biosignatures to the broader implications for our understanding of life in the universe, we've covered considerable ground. We've contemplated what makes a planet habitable, what Hycean worlds might be like, what it would mean to find life elsewhere. We've thought about the technology we use to study distant worlds, the philosophy of contact with alien biospheres, and the long view of cosmic time. The question we opened with, whether K2... Before I say goodnight, I need you to know something. When this video was posted, most people scrolled right past it. They saw the length, they saw the topic, and they kept scrolling. But you didn't. You stayed for 2.5 hours, you chose depth over speed, and wonder over noise, and I think that says something beautiful about the kind of person you are. If this channel has given you something tonight, a little more peace, a little more wonder, a little more understanding of the world you live in, then a like and subscribe is the kindest thing you can leave behind before you sleep. Not just for this channel, but for the next person out there tonight who needs exactly what you just found here. Now, rest. You have earned it. The question we opened with, whether K2-18b truly hosts life, remains unanswered definitively, and perhaps that's appropriate. Science doesn't always provide immediate closure. The answer will emerge over years of additional observations, refined models, accumulated evidence. The 99.7% probability we've discussed is not certainty, just a measure of which models best fit the current data. Time and further study will tell us whether this probability holds or shifts as new information arrives. What we can say with confidence is that K2-18b represents a frontier, a place where our knowledge meets the unknown, where observation meets interpretation, where speculation grounded in evidence meets the genuine mystery of whether we share the universe with other living things. Whatever the final verdict on K2-18b's biosignatures, the planet has already taught us that Hycean worlds exist, that sub-Neptunes can maintain conditions potentially hospitable to life, that the search for living worlds must cast a wider net than simply looking for Earth twins. Wherever you are in the world right now, whatever time it is where you're listening, I hope your breathing has slowed over the course of this exploration. I hope your thoughts have quieted, that the concerns of the day have receded into something manageable and distant. I hope your body feels heavy and warm and ready for rest. Look up at the constellation Leo if you can, if the sky is clear and dark where you are, or imagine it if you cannot. That great celestial lion stretching across the sky, somewhere in that constellation, invisible to our eyes but real nonetheless. A red dwarf star shines with its dim, reddish light. And orbiting that star, a planet slightly larger than Earth makes its 33-day journey, wrapped in hydrogen, possibly covered by a global ocean, perhaps harbouring life in its dark depths. All those photons travelling across the void right now, 26 years into their journey from K2-18 to Earth. Carrying information we'll analyse in 2049 about what's happening on that distant world today. All those potential organisms, if they exist, going about their existence in an ocean beneath a hydrogen sky, unaware of us as we were unaware of them until so recently. All that chemistry and biology and evolution happening across impossible distances, connected to us by nothing except the shared fact of existence and the light that travels between. There's a peculiar peace in acknowledging how much we don't know, how vast the universe is, how small our knowledge remains despite all our progress. K2-18b might have life or it might not. The dimethyl sulfide might be real or it might be noise. The ocean we've imagined might exist exactly as we picture it or might be completely different from our models. We might confirm biosignatures within a decade, or the evidence might remain ambiguous for generations, and yet the search continues, patient and methodical, driven by that fundamental human need to know, to understand, to push back the boundaries of ignorance just a little bit further. The telescopes will continue observing, the scientists will continue analysing data and refining models. The slow work of understanding will progress at its own pace, indifferent to our impatience, responsive only to evidence and logic and the accumulation of knowledge over time. In the end, what we're left with is not certainty but possibility, not proof but evidence, not answers but better questions. We've learned that planets like K2-18b exist and can be studied in detail. We've learned that the signatures of life, if life exists there, are potentially detectable across light years of space. We've learned that the universe continues to surprise us, that our expectations about what's possible continue to expand, that each answer we find leads to new questions we hadn't thought to ask. Sleep well tonight, knowing that the cosmos is vast and strange and full of wonders we're only beginning to understand. Dream of distant oceans and hydrogen skies, of light travelling across the void, of organisms adapted to environments we can barely imagine. Dream of our place in this enormous universe, neither central nor insignificant, but part of something larger and older and more complex than any single mind can fully comprehend. And when you wake, the universe will still be here. Still expanding, still evolving, still full of mysteries waiting to be explored. K2-18b will still be orbiting its red dwarf star. The James Webb Space Telescope will still be gathering light from distant worlds, and will still be asking questions, still seeking answers, still reaching across the void, with our instruments and our curiosity, and our stubborn refusal to accept ignorance when knowledge might be possible. Good night.